All right, so it's 2 p.m. We can start the session. My name is Mohit. I'm the second guy there on the screen. Unfortunately, Ghassan could not make it. Yesterday, he had issues with his flight. So his flight was delayed and then canceled at the very end, which implies that I'll be doing the tutorial by myself. We'll have a 15-minute break in the middle, which is going to be very helpful to my voice. But apart from that, I'm quite well versed with all the materials of the tutorial. Both of us, Ghassan and I, have worked for a while. I'm a postdoc in his lab. Pretty familiar with the context. What we'll be discussing today is robust image understanding. And specifically, we'll be discussing about three things: explainability, uncertainty, and intervenability. And the outcome of this, hopefully, is that I will convince you that all these three things are very similar to each other. Having one implies that you'll have having a good knowledge of uncertainty means that you will have a good knowledge of the explainability of a neural network. Having good knowledge about explainability of a neural network implies that you can intervene within a neural network's working process, even though you're not the engineers or researchers who actually made, let's say, the network, right? So these days we have neural networks that have more than 1 trillion parameters. ChatGPT, the 4.0 version, which I don't think is still available for everybody online, but that essentially has about 1.76 trillion parameters. So it's not easy for anyone to just go through and try to work with it. Everything that we'll be discussing today is more from an inferential perspective. That is, once a network has been completely trained, how do we go through and try to understand it, try to interpret it, and what is required from a user perspective to understand these large parameter networks. Now, everything I'll discuss is more from an image perspective, but the same thing applies to any other multimedia application. So we have work on similar things on, let's say, text and natural language processing as well, and a little bit into LiDAR processing and radar processing as well, but not as much. But most of the things that we'll discuss today is from an image understanding perspective. All the tutorial materials that I'll be talking about today is present on our website. So essentially what I mean by the tutorial materials implies the slides that we're using. As you can see on the bottom left corner over there, it says 180 slides. I wouldn't worry too much about that. There's a lot of slides which are hidden. There's 30, 40 slides that are hidden. So I would say that this tutorial will extend to about 2.5 hours. And based on interactivity after that, in terms of questions, we can have a little bit more. And I want to stress on the last part. So this is not like a very formal lecture session. I hope that everybody will stop me in the middle and ask me questions. Again, that will help my voice as well. So it really does help me in trying to give the tutorial. So if anybody has any questions, you're more than welcome to stop me in the middle and we can go through those points one by one. All right, so I like to start these things just by looking at memes. So we have this expectation of what a neural network is, of what deep learning architectures are. I'm sure every one of us has gone through and heard about deep learning in the last few years. Since 2011, that is everything that people talk about in machine learning, right? But once you go through and dissect this neural network, it's not as well prepared as what you see on the left-hand side. The expectation versus reality that you have these kind of meal prep memes applies to neural networks as well. So the first part of the tutorial, we just discussed very quickly the working of a neural network, and then we will go through and dissect and see what works and what does not work. This was a very famous example a few years back when we were discussing about vision applications and the problem with vision applications. On the right-hand side, you see a combination of dogs and blueberry muffins. Now, it takes us a while, a couple of seconds, to go through these images and identify which are dogs and which are blueberry muffins, right? It's not very easy just by looking at it to say that one is the other. In fact, it might, even for us humans, there is a little bit of confusion involved over there. Just imagine what it is for neural networks. This is where the aspect of robustness comes in. We want to make sure that neural network is able to reflect on looking at this image and say which is a dog and which is a muffin. On the left-hand side, you have these problems accentuated, not just in these kind of human problematic instances on the right-hand side, or at least to my left and your right, but the stop sign that you see over there small types of perturbations added to it, like shearing effect, creates these kind of problems within a neural network's recognition process. And this is an issue for deep learning architectures. This idea of robustness is an issue. So what is required of a deep neural network? Well, we want it to be as robust as possible. And what that essentially means is that given a neural network, it should be, and given a neural network that has been trained on pristine conditions, it should expect these kind of additional problems to occur at inference. So let's say you're training an autonomous vehicle agent, and on perfect settings in clear weather, there's no clouds, the sun is shining, it's the middle of the afternoon, everything is working well. But you cannot expect the same thing to happen even at inference. So when at testing or deployment, in this particular case, what you're seeing right now is blurriness. So you have a blurry camera, and you want to make sure that images or the video that you're getting from these blurry camera is also recognized very well. In this case now, I think you're seeing rain. So this is something that is required from a robustness perspective. And this is what we're going to be calling as novel data. Anything that a network has not seen at training is going to be a novel data. So in this particular case, novel data can come from some kind of anomalous settings. It can come from out of distribution data, or there's something called adversarial images, and it could come from that aspect. All of these things we're going to be discussing throughout the course of this tutorial. But the important part here is the umbrella of the novel data, which is at inference, a network might be able to find, or it might encounter these data points that are not specifically, it has not been trained for, it does not know how to handle. So it is something that we have to make sure that it knows that this is not something it has seen, and it should be able to make the best possible recognition at that point. So everything we'll discuss is from this novel data point settings. Now, you might be asking that in most cases, we want to make sure that we want to use these novel data during training itself. Yes, we know that rain occurs. We know that snow occurs, blurriness occurs. So why don't we just use that during training itself? And the answer is that it's not always clear how to use these kind of novel data during training. So let's divide the training into two aspects: the early stage training and the later stage training. So let's look at the first scenario, which is the early stage training. So on the left-hand side, you see a network that has been trained with slightly increasing number of samples. And these samples, we are going to be saying, is either very easy set of samples or novel set of samples. So so let me use this. Hopefully I'm not impeding anybody's thing here. So let's say this is all my data points, and I have two particular classes. One is the gray classes here, and another is the blue classes, right? This is how it is. Let's say that in the beginning stage, I only have access to two samples from the class 1 and two samples from class 2. It's my choice on which I will choose the sample. So it's like an active learning setting, if you're familiar with that. But even if not, it's just I'm going to choose two samples from each class in order to train my network. Let's say I make the decision of choosing these two samples here and these two samples. Now, this is a toy example, so I'm making this assertion that I'll choose these two samples because I know by looking at the data that these two samples are the easiest samples, or the ones that are in the center of their clusters, right? These gray samples here are the center, and the blue samples here are also at the center. So when I train a network, which is basically just a simple decision boundary on these two samples, it goes somewhere here. And this means that its accuracy is very high, right? The only thing, so everything on the left-hand side of this boundary here is gray. Everything on the right-hand side is blue. The only thing that is incorrectly classified is this one thing, which implies that the accuracy is going to be very high, right? So easy samples, or not novel samples, when you're using it to train in the initial stages, your accuracy will increase rapidly. From a more technical perspective, this actually is the amount of information that you're providing. If all the data points are providing the same kind of information, which we see when it's in the center of a particular cluster, network doesn't have too much to train, essentially. It doesn't have bigger problems to train. And so what happens is that the accuracy for those samples increases quite well. Now, if I have a high information type of samples, which is here at the bottom, so let's say I'm choosing these two outliers or novel data during training in my initial stage, and these two are outliers in the blue region, right? So what you'll notice here is that the classifier now goes through the middle, which implies that there's a lot of non-accuracy. So anything on top of this classifier is gray, anything at the bottom of this transfer classifier is blue. So everything about this is blue things here is incorrect, and all these gray things here are incorrect, which implies that the accuracy is going to be very bad. Right? So it is not clear for us to choose these data points by saying that, oh, I want to have novel data at training. By definition, in fact, you're not even going to sometimes have novel data during training. So let's say now I'm going to be thinking about, okay, why don't I train with easy samples in the beginning and then train with novel samples at the very end. This is also problematic because of this concept called catastrophic forgetting. If you've not heard of catastrophic forgetting, the idea of catastrophic forgetting is that if a network has been trained with a certain amount of data, as soon as you now train it with a different, let's say, task, it's going to forget the first task. So in this particular case, let's say we started by training with something called fashion MNIST, which is also a very, very simple data set. And then after about 50 epochs, we start training with MNIST data set. It's basically a similar classification task, except that now we have a different amount of different data. So the number of classes, everything is very similar. Ideally, at the end of 100 epochs, I want to have learned everything about fashion MNIST, and I want to have learned everything about MNIST. In fact, I'm sorry, I think it's the opposite. First 50 epochs, I train with MNIST dataset. The next 50 epochs, I train with fashion MNIST dataset. So what you see here is that initially, your MNIST data is getting very good results, close to 100. And you have not trained with fashion MNIST, so it's getting close to 0%. But after 50 epochs, you train with fashion MNIST, the fashion MNIST goes up to about 80, 82%, which is kind of par with fashion MNIST data. But your MNIST data set now goes down. And this is where the catastrophic forgetting comes in. As soon as you add novel data during training at the later stage, it will forget whatever it has learned at the initial stages. So this shows that this kind of novel data, it's not very easy to know where and when to apply it during training. If you apply it in the very initial stages, you're really not going to train anything at all. If you try to put it at the later stages, your results are going to decrease and you're going to forget whatever it is that you have learned initially. So it's not always clear how to handle this novel data at inference. And that is why we are saying that you have to handle it at inference rather than during training. So novel data basically pack this 1-2 punch. Essentially, you might not have access to novel data. But even if you have access to novel data, you don't know when it needs to be part of your training. Is it at the beginning? Is it the end? It's not very clear. And this is a problem for novel data, essentially. And this is why we say that we have to handle this novel data at inference. We have some kind of model training, and then we have some kind of inference, which is novel data. This is actually an actual image. So we have always seen red stop signs. I'm not sure how many of you know this, but if you go to national parks, your stop sign is going to be green. And a network that has learned on just normal stop signs is going to look at the red color and then know it's a stop sign. It might never have learned about STOP. It has just learned about the shape and the color. In fact, we'll talk a little bit about this later down the line. But as soon as it sees that the color is different, maybe this is something that it's not going to recognize. And it could be problematic, right? If you are not able, an autonomous agent is not able to recognize a stop sign, which is very, very impactful during a driver settings. All right, that was more like an introduction into what we are doing. The tutorial itself will have about 5 parts. The first one, we just discussed very quickly about what inference is in neural networks. This will be followed by the idea of explainability in neural networks, followed by uncertainty and intervenability. Parts 2, 3, 4 are, I would say, the meat, or if you're a vegetarian, the broccoli of the entire tutorial. The first one and the last one are more, your entrees and appetizers, essentially. We'll go through that quickly. Again, if anybody has any questions, you're more than welcome to stop me in the middle. All right, so let's start about the first part, which is inference in neural network. We'll essentially talk about 5 major things. We'll talk about some basics, what we mean by robustness, followed by some challenges, as well as how we're going to be utilizing gradients at inference. So deep learning, as you all know, is this kind of a cascaded system where we are extracting important information across different layers. So if we think about it as low-level features, mid-level features, and high-level features, low-level features are dependent on just simple things like edges and color. And this is something that we knew in information processing, video processing, image processing for a long, long time. The edges and color are most important perceptual components that exist. But once we come to the middle layers, it's a combination of these perceptual components. So you'll now start seeing a little bit more higher order shapes. You'll see circles, you'll see squares, you'll see different kind of a texture patterns and so on. But as soon as you come to the last layer, you'll actually start seeing objects themselves. So there are certain weights that are tuned towards certain objects, let's say a teapot or a giraffe or any kind of animals. You might actually start seeing this on this stuff here. I don't know if it's easy to see, but this is the head of a bird. Again, this is a very common example. You can see the beak here, eye, head, and stuff like that. So essentially, you'll start seeing semantically recognizable concepts at the very end. And the underlying computation of a neural network, extremely simple. It's nothing more than a bunch of weights which just multiply with your input. And there is a very important non-linearity, which we call an activation, at the very end of every single neuron. All these neurons are now combined in different ways to construct multi-layer perceptrons, convolutional neural networks, transformers. It's all based on these very simple neurons. And all the techniques we're going to discuss today is going to be applicable to everything from MLPs, actually not MLPs, but CNNs and transformers are going to be part of it. So this here is more of a how artificial neural network started, which is an MLP, just a set of cascaded neurons, all of which are constructed into layers, and then layers are now stacked one on top of the other to have multiple levels of these low-level, mid-level, and high-level features. There might be many hidden layers, and again, if you're familiar with ResNet architectures, there's a ResNet 18 and a ResNet 151. So the same type of modules which are repeated over and over again to give you a certain network. A very important part of the idea of image processing was in convolutional neural networks when we use the stationary property of images. Stationary property of images essentially implies that different parts of the image are based on the same set of basis functions. I can decompose top left corner of an image, bottom right corner of an image, based on the same set of basis functions. We see this in discrete cosine transform, let's say, when we are doing JPEG compression, where based on the same 64 DCT coefficients, I can represent the top left corner and bottom right corner. It works very well. And we want to utilize that thing within neural networks, and that's where stationary properties comes in. So instead of a bunch of neurons for every single pixel, it'll be a bunch of convolution kernels at every single patch. And that is how we start modifying this in a patch-wise fashion. So now that we have a very basic grasp of neural networks, let's ask ourselves, what is inference? In fact, we'll ask ourselves 3 questions: what, where, and when is inference? The statement comes from the famous Avengers movie. If you know it, then you know where the what, where, when comes from. So inference is essentially the ability of a system to predict correctly on novel data. So given a trained model, which you see here in the box, and given some, let's say it has been trained on cats, and now you're given a cat which is actively trying to hide itself. And in this particular case, it's there within this kind of Amazon box. And its color is also similar to the box. So it might become a little bit harder for the network now to recognize that it is the face of a cat, essentially. So this is essentially what is inference. We don't have access to what kind of data is available to us. So any kind of data might be shown to the network, and it should be able to infer on it. Generally, when we discuss about inference, it's usually on the last layer. Now, this is where transformers, let's say, differ from that of CNNs and RNNs. Usually in CNNs, we have the data point that goes in. Sequentially, it is processed, and by sequence, I mean layer by layer, it is processed, at the very end of which you get an output called a cat. So this is essentially what you have. A cat goes into the input layer and across different layers in order to get your output, which is a cat. In transformers, generally there are different heads, and all of this processing happens at once, and then it's combined. But still, you have a very end, you have this kind of a aggregation module that aggregates everything and spits out one number that is going to tell you that it is a cat. So essentially what this means is that the required information is learned at training, but it leads to this inductive bias at testing. And by inductive bias, I mean that any kind of patterns that has been used via training is going to be used at testing as well. It's a property of neural networks where we can feed in this kind of data in order to construct the inductive bias, but in some cases it might not be beneficial, especially in this novel data scenario. So when we talk about inference, there are two kinds of inference. One is testing and the other one is deployment. And we'll discuss about both these things. Whenever we show numbers and tables, it's always the testing aspect. But conceptually, we are always thinking of it from a deployment perspective. So, during testing, we have a large data set of test set, we pass it through the network, and we want to make sure that it's cat or every single instance. We'll use that for determining what the accuracy is, what the F1 score is, or other performance metrics. But the overall goal for us is always the bottom part here. We want to deploy this for users to use it. And during that test time, during that inference, just a single image is going to be shown to the network. And you want to make sure that the output is correct, which in this case, it needs to be a cat. So there is this difference. The evaluation criteria is usually in the top one, which is testing, but usage criteria is always in the bottom one, which is deployment. Now, we'll be talking about one specific application. Again, deep learning is such a large field. It is very hard to cover everything, even if we have 2-3 hours. We'll be talking about one specific application in this case, and maybe a second one of segmentation, but most important one is the idea of classification, because it's probably the one that is the easiest to grasp. Given a certain network, you pass an image through it, and you get output. In this case, it is going to be a cat. Let's look at some of the terms that we'll be using throughout today. So, So whenever I say logits, that is the last output from the last layer is what we would call logit. So essentially, let's say you have a network that is trained on ImageNet. ImageNet has about 1,000 classes. So the output of a neural network is going to be 1,000 cross one vector. And that is what I mean by logits. Predicted class is usually the maximum of my logits. I get 1,000 cross one vector. I run a simple argmax algorithm on top of it. The output of an argmax is what my predicted class. If I run a softmax probability on top of the logits, then we are going to get probabilities. Again, softmax is not the best probability measure, but we'll talk about other measures that exist, but it's the easiest to think about. Train network is the F, and training data is this capital Chi, capital X that we will be using. But during inference, we'd only have access to one X, which is belonging to some distribution. In this case, it belongs to the training distribution, so it's not technically novel. But sometimes you have data points that don't belong to that distribution, and that is when we would call this thing as novel. And again, the novel data could be part of noise, it could be part of adversaries, it could be part of out of distribution, and everything else that we discussed in the beginning of the slides. All right. So to achieve robustness at inference, the most important thing that we require is sufficient information. Information is something that is very, it's not easy to define unless you take an entire 3-month course on information theory itself, because generally what we think about Shannon information, generally what we think about information is Shannon information, and it might not be as useful in these kind of settings. So we'll spend a few minutes talking about what information we are discussing. And then it's important to also know that the methods to extract this information is very neural network dependent. everything that we have initially in terms of before, let's say, 90s, in the 2000s, the kind of information available to us or information methods available to us are not always applicable to neural network architectures just because of the size, the growth within this particular community. And so we also need to discuss the techniques of information retrieval for these kind of deep neural networks and architectures. So we'll start by discussing why this is challenging. And this is kind of a toy example. So in this particular setting, manifolds are a very important concept within neural networks. Every single layer at the end of it, we have the outputs, and we call that as a manifold. If there is and the reason we call it as a manifold, because you have these networks are very, very large, right? 1.76 trillion parameters. That's how we started with. So if I think about a space which is 1.76 trillion parameters, we can only imagine three-dimensional spaces. So it's impossible for me to tell you to imagine that kind of a 1.76 trillion parameter space. The good thing is that data doesn't exist in that large space. What data exists in is a much smaller space within this kind of, and much more structured space within the 1.76 trillion parameter space. And that is essentially what we call manifolds. So I'm very sure that you would have seen images like this throughout. The way we obtain this particular image on the left-hand side is we know the exact mathematical modeling of at every point what L of theta, which is the likelihood, at every point what this L of theta is. If you have a mathematical model, you can define this left-hand side. Let's say you don't have a mathematical model, which is true for the deep learning network. Generally, what we do is feed in a million images. You get an output, and then you plot this. In this case, I think it's based on isomath. And based on that algorithm, you can define, or you can find what this manifold is going to look like, or at least visualize what this manifold is going to look like. On the left-hand side, you have the exact mathematical definition. And on the right-hand side, you just have so much data that you're able to construct this manifold. And that's why deep learning works. You know that there is so much data, and you will use it in order to construct these manifolds. The problem is that at inference, you don't have access to either of these things. You don't have access to exact mathematical model of your deep learning network, and you don't have millions of data points at inference. Ideally, at training, this is what we have. The millions of data points kind of construct this manifold, so you have access to everything. You know that this cat, which is in distribution, is present in the middle of this topological feature. You know that a cat hiding itself is away from this topological distribution, and you can construct some kind of distances between these in order to understand or interpret your results. But what we have in practice is the left-hand side. We have a neural network that has been trained, yes, but we don't know much about that neural network. It's still a black box, right? We don't know the exact mathematical definition, nor can we construct something on the right-hand side based on millions of data points. That is why this is very challenging. We cannot easily extract data or information at inference for any given neural network. And that is why we have kind of, how do I say this, like hidden part of the network, the module over here. And that's why we say trained network knowledge is not easily accessible to us. So what can we do about it? Well, this is where the idea of Fisher information comes in. Now, we discussed before about Shannon information and how it is not as helpful to us. And that is because the more helpful information for us is the idea of Fisher information. Because let me again state that what we have access to is a trained model, but we know nothing about that model. The information that is required or that is useful in understanding a trained model is something called Fisher information. Given a network, passing an image, you see the output. The output of that is Shannon information. But if you want to know about the model itself, that is where Fisher information comes in. And what Fisher information tells you is this is about the theta. So about the parameters that exist, it gives you an idea about the theta in this particular case. So Fisher information is defined like this. It's variance of dou by dou theta and some likelihood function L of theta given x. Now, the important parts here to remember is the dou by dou theta, which is where the gradients come in. And that's going to be a theme, central theme throughout the next couple of hours of the talk, where gradients are important for us, gradients with respect to theta, which is the parameter. So given some kind of a statistic, I'm going to, let's say, assume a statistic for the manifold, even though I don't know. I'm going to pass some data points through it and get this gradient in order to find what the best approximation of that grade, of that parameter at that point is going to be. Right? So the variance of that parameter is going to give me Fisher information. Now, Fisher information is a surprise in a system that observes an event. Again, just to make sure we are very clear, Shannon information is the surprise in the event itself, but Fisher information in the system through which the event is passed through, or in which the data point is passed through, that is ideally Fisher information. Now, this is a very, very important statement, but I don't think I've motivated yet. But Fisher information, the reason we use it is because at inference, given a single image from a single class, we can extract information about other classes as well. So given the image of a cat, if your network has learned about dogs, you will be able to extract information about the dog as well because of Fisher information. Again, I have not motivated this enough. So when we come to explainability, I will be able to show you visualizations of this particular statement. And this particular statement is very, very, very important and is going to be a cornerstone of the entire talk tutorial today. Again, just remember this. We'll bring this slide back and I'll motivate visually better this particular sentence. So the way Fisher information works is by giving us one data point, you'll be able to extract some local information. So you don't need millions of data points. Given a few data points here, you'll be able to try to understand this kind of loss manifold that might exist. Again, I want to be very clear. You can approximate the loss manifold based on a few points rather than obtaining the entire manifold based on millions of data points. The exact math is not that important, but essentially what is important is the gradient with respect to samples. That is something that we will be discussing throughout the talk. So gradients draw information from the underlying distribution as learned by network weights. The knowledge is already present within the network. Our goal is to extract it. And what we are saying here is that gradients are a good measure of the knowledge that exists within a neural network. So this is where we just start off with this kind of explainability. So what you'll be seeing in explainability is visualizations like this. Given this image of a dog, your gradients can infer information about statistics of the underlying manifold. So we know that around, if this data point, this dog, exists at this manifold, we'll know some local information about that manifold. We'll know about the features that can exist in a dog. We can know about, let's say, the face of the dog, the nose, the jowls, the different features that might exist in a dog. All of them we can basically get based on using the gradients. And this is where the feature attribution via GradCam can come in. So GradCam is a method of explainability. We'll talk about that later down the line. And we'll be using gradients in order to extract this kind of information. So why are gradients important? Well, the first one is we just saw, or we'll see even more down the line, which is it gives you some kind of local information around the projection where the novel data or the training data can exist. Importantly, it gives us a way to traverse through the manifold. Now, if you know anything about gradients during training or the idea of backpropagation, you know that gradients are very, very important during backpropagation algorithm. It is the way that you can go through and try to construct your neural network. Given a manifold, even without knowing anything about the weights, without the manifold, gradients will give you certain directions. It'll tell you where to go and traverse within this manifold. So we have already seen that we don't know anything about this manifold. So by taking gradients, it will tell us that if you go to the left-hand side, maybe you might be onto something. If you go to the right-hand side, it's not good at all. Please don't go there. But if you go at the bottom here, which is represented by this blue line, it is something that you would wish to do. That is where the local minima exists. So it tells us something about the space, the topological space of something that you have no access to, about the knowledge you have no access to. So the negative of this gradient, it provides the descent direction that we can use in order to understand the network manifold. So in the next two parts, the way we will be looking at this is we will extract this local information and we will try to change the manifold ourselves at training. And that is essentially what we'll be discussing in explainability and uncertainty, because this is what existing methods do. You don't know much about a network, so let's just reconstruct a different one and see what the difference is between an unknown manifold and something that I know. So that is essentially what we do in explainability and uncertainty. And in intervention, it's like we are intervening within a neural network and asking it to traverse to different spaces. And in both of these cases, your gradients are going to help you. So we'll never get that, the entire manifold, we'll never see it at inference. But what we will see is small portions of it, either local understanding or more understanding of how you can traverse through your network. And that is essentially what we're going to see in the next few parts. All right, so with that, we come to the next stage, which is about explainability at inference. So I think I'm on time. So essentially what we will discuss is about visual explanations, and we'll go through in more detail about that one method that we saw before, which is GradCam. And based on that, we can have multiple other methods, counterfactual cam and contrast cam. So we'll see these three techniques, and then we'll have a case study about what they are. Oh yeah, we had this paper about a couple of years back in Signal Processing magazine, explanatory paradigms. And the reason we call it explainability paradigms is explanations or visual explanations are nothing more than answers to your questions. So it's instead of thinking about, oh, these are the techniques of explainability, it makes more sense to think about what is it that you want out of explainability. So given this image of a bull mastiff here on the left-hand side, if your question is why bull mastiff, then your visual explanation has to be different from another kind of a question, which is what if the bull mastiff is not present, right? So the first answer is pretty straightforward. It's a bull mastiff because of the existence of this face. Now, if my question is what if bull mastiff was not in the image, the output would have been a cat. And the answer for that is based on this visualization here. It is highlighting the regions of the cat which it would have used in order to make the decision. Now, let's say you're more interested in a fine-grained question. So you have this, why bull mastiff rather than a boxer? So you know what a bull mastiff is, you know what a boxer is. Now you're trying to understand what is the difference between the two. And if the network is basically showing you the jowls. So this is where the difference exists. The jowls of a boxer is much more different than that of a bull mastiff. It's more heavier, essentially. So the fact that that was different is what your network is showing you. So these kind of questions are something called correlation explanation, counterfactual explanations, and contrastive explanations. And those words come from the questions themselves. Why P rather than Q, where P and Q are certain predictions, more from a philosophical perspective, are contrastive explanation. Any question that is something like what if is a counterfactual explanation. You can have anything after that. What if dash, that would be a counterfactual explanation. Why P rather than Q would be a contrastive explanation. So all three of them combine to form these kind of paradigms within explainability framework and what would be, in this case, visual explanations and characteristics. Why are they important? Because again, we are discussing from a deployment perspective, and at the end of the day, we don't know who it is who are going to be using it. Let's say a kid is trying to use our algorithm. So the kid is going to be asking, given this image of a spoonbill here, the kid is going to be asking, what is this particular image? The network is going to say, oh, it's a spoonbill. Now, that's insufficient for everybody, right? You want to interpret your results. So the kid is going to ask, okay, why is this a spoonbill? And the answer to that should be that there's a pink and round body, there's a straight beak, which basically shows everything that you need for a spoonbill. And the kid is going to trust you. It's going to trust, kids are trustworthy. So the kid is going to say that the network taught me about spoonbills. But let's now come to an ornithologist who has knowledge about spoonbills. So this ornithologist is now interested in, okay, why spoonbill rather than something like a flamingo? And the answer is that there is a lack of S-shaped neck in my spoonbill. Now we know two things about the difference between spoonbill and flamingo. Actually, I did not know before until I, did this and we had to look it up. But essentially, there are two differences. One is the shape of the neck, and another one is the shape of the legs. Both of them are what differentiates a spoonbill from a flamingo. Now, the network is showing you lack of S-shaped neck. So now the ornithologist can say, yes, true, your network is right. The neck shape is different, but it probably does not know anything about the change in shape. So what that helps you, or what that helps the ornithologist, is to assess the network. Say that networks know some things while it does not know other things. This is where, again, the explainability and paradigms of explainability become very important. The question, instead of just asking why spoonbill, which would be this kind of a correlation explanation, you're now asking why spoonbill rather than flamingo, which is a contrastive explanation where the context and context comes into picture. Of course, if a fox asks why spoonbill rather than a flamingo, you expect all parts of the flamingo to be highlighted because they both are very different from each other. It cannot be exactly the same thing, and this will help the fox trust the network. So this is like a cartoonish way of trying to get the point across that the idea of explainability is very contextual dependent. It's dependent on who is asking the question, and that is where the context comes in. And the network must be able to give any kind of an answer. And that's a very broad statement to make. It should give any kind of an answer. And this is where we look at something called reasoning and try to decide, okay, these are the kind of questions that can be asked. You can ask a contrastive question or a counterfactual question or a correlation question, and a network should be able to answer all these things. Now, we started by talking about gradients, and we said that gradients are very important. So again, just to be very clear, all the explanations that you see here are generated. It's not something that we just went through on an iPad and drew the results. It's something that has been generated, and we are showing it here. All of them are dependent and use gradients in their methodology itself. There are a number of gradient-based methodologies. The simplest ones are the three listed here, which is vanilla gradients, deconvolution gradients, and guided backpropagation. There's very small changes between them. I won't go deep into the way it works itself, but essentially vanilla gradients, you're just backpropagating the output, the prediction, until the very beginning in your first layer, and you're just outputting and showing that output. So you have a cat here. If you put this through a network, you get a prediction from the logits. You backpropagate the logit of a cat. So in that 1000x1 vector that we discussed before, one of them is a cat, and you backpropagate that cat logit. At the very beginning, this is how the gradients are going to look like. Deconvolution gradients, there's a little bit of change compared to vanilla gradients. You're only looking at the positive examples of your gradients. You're going to be removing all the negative ones. You're going to be using the positive ones in your backpropagation. Guided backpropagation is like a combination of vanilla and deconvolution, or I would say it's double deconvolution, where you're going to be using only the positives both in the forward and backward direction. The exact methodology of these is not as important because it's not class discriminative. We'll never be able to show you these kind of examples, these kind of asking questions and give you results based on any of these three examples. And this is where the I would say better kind of explanations come into picture. The first one of which is GradCam. Now, if you've studied explainability literature, GradCam is probably the most well-known explainability method that exists. We'll go through very quickly about what GradCam is and how we can use GradCam to obtain these explanations, it's actually very simple and quite straightforward. And the reason it's very popular is because it works with everything. CNNs, transformers, any kind of an architecture, it does not matter. Even the kind of data does not matter as well. You can use this for images, you can use this for text, you can use this for any kind of data modalities to begin with. The way it works is, I'm sorry, I'll be looking at the image here in order to make sure that my pointer is there. So you have an image of your dog. It passes through the network. And you can think of this particular network has multiple convolution blocks, followed by some kind of a last convolution block, and then followed by this kind of a task-specific thing. So until this point, again, GradCam is something that is used for image classification, segmentation, video understanding, any kind of a multimedia application, GradCam works. So, but at the very end of most of these neural networks, you have a very task-specific thing, and that's why it's written that there is a task-specific module. And the final layer is nothing more than a bunch of fully connected layers. And the output is a set of logics. So you pass this image, you get the output that it's a dog, you backpropagate that particular dog, and that is what you see. So the black lines here are the forward propagation. The blue line over here is the gradients or the backpropagation. We backpropagate the logic for the prediction, in this case, the dog, and you get that here at the convolution layer. Generally, we look at the last convolution layer, and this is what you get. So gradients, essentially, for every single parameter, you have a gradient. So for a convolutional module and a convolutional feature map, you have the exact same size, you have a gradient. That's why you see about 6 rectangles here and another 6 rectangles here, right? It's because the fact that every single parameter has a gradient associated with it. Whatever shape your original parameter is, you'll have the same shape for your gradients as well. The way GradCam works is it basically takes the YC here is the prediction, which is in this case a dog. Dou Y by dou A here is the activation, which is the activation maps here, the convolution maps. Dou Y by dou A is nothing more than your differential of your output with respect to your activation, which is the gradient maps that you see over here. And you have a double sigma, double summation, which implies that in the X direction and Y direction, you're just going to sum it up. So for a rectangular convolution module, you're just going to sum it up in the row and Y column. And this entire blue channel here, you're going to get a single number. That is what you see. So instead of 6 rectangles, you now have 6 numbers, which is basically what you have in your alpha. So this is where the gradients come in the GradCam. Grad in GradCam is the gradients. It's nothing more than a sum of all your gradients in a particular channel. Once you get that sum alpha k, you're just multiplying your original feature maps with that alpha k. So this blue multiplies the last channel, the red multiplies the first channel, and so on. GradCam uses these gradients as weights, as some kind of an alpha weight parameter, and multiplies the feature maps that exist in the convolution network. And that's it. You have a ReLU. ReLU is a rectified linear unit. Anything that is less than 0 becomes a 0. Anything that is positive is kept the same thing. So this entire thing is GradCam. And the output of this for this dog image is going to look like something at the bottom here. Hopefully this makes sense, because the dog's head is at the top position. So the highlights are at the dog's head. And that is what we want to see. We want to see that the network is looking at the dog's head in order to make the decision that it is this particular breed of dog. Of course, the final stage is that it needs to be upsampled. The idea of a convolutional neural network is that it starts off as a big image, but your network sees different parts, different patches of the image, and recognizes the patterns, so that at the end of the day, a large 224 cross 224 cross 3 image boils down just to a single number, which means that there's a lot of compression that keeps on happening through the network, which implies that this feature map generally is very small. For a ResNet 18 architecture, I believe this feature map is just 7 cross 7, while for something like a BGG 16 architecture, it's It's a 14 cross 14. So generally people who use GradCam, they show you results on VGG16 because the results are a little bit more fine grained. Your 14 cross 14 math is upsampled back to the original size of the image, which is 224 cross 224 image. So if it was a ResNet 18, then a 7 cross 7 image is upsampled to 224 cross 224, which means that this kind of a red image is not easily visible. Everything that I showed previously was based on VGG16 because you'll have more of a fine-grained thing. If I had used ResNet 18 to get these images, I'm very sure that this entire right-hand side portion would be red. So you wouldn't have been able to see the difference in that neck in this particular case. All right, so that is GradCam. Now, it's a very popular technique because you can use it for image classification, image captioning, visual question answering, NLP tasks, any module, it does not matter, right? Because these layers are going to remain the same. Usually the task-specific layers are going to be different. And you don't even need convolution layers here. Anything, layers that are stacked on top of each other, your gradients are going to be the same size. So you can combine them to create that alpha parameter and just multiply them. So even with transformers, when you have your key value query pairs, you will be able to use GradCam in order to get some kind of explanations. Again, in transformers, you'll have attention directly. You can show it, but GradCam is also a good way of interpreting transformers. Now, this is generally what we refer to as observed correlations. We have these questions called YP. So in this case, it was Y bull mastiff, and the output is the head. This is what we saw, right? So GradCam answers the first paradigm, which is Y bull mastiff. Now the question becomes, what can we do about the other two, which is the counterfactual observations and the contrastive observations? How can we generate explanations for these two questions? So it's very straightforward and similar to GradCam approach. For the counterfactual cam, so something that answers the what if questions, the only difference from GradCam is that we backpropagate the negative of the logit, the negative of the dog, right? So the prediction is Y of C, which is your logit. If I'm backpropagating Y of C, the weights which is alpha is going to show why the YC, where the YC is going to be within the convolution kernels. If I take the negative of YC, it's basically going to discard everything that pertains to YC and looks at all the other important regions within the particular image. So if you backpropagate the negative of prediction, you will be able to get this image, what you see here on the left-hand side, which is going to be a counterfactual cam. It answers the what if question. Similarly, you have this kind of a contrast cam, YP rather than Q. Given a prediction P, you're likely to ask the question, why cannot it be Q? So it makes sense. Why spoonbill rather than flamingo? Why bull mastiff rather than boxer? These are the kind of questions that you'd be able to answer using contrast cam. And the way you would do it is, instead of backpropagating the logic, the prediction logic, which is YC, you're going to be backpropagating the loss function, J of YC given some kind of a contrast class, J of P comma Q, where P is your YC, which is your prediction logic, and Q is your YQ, let's say, which is your contrast logic. And J can be any kind of a loss function. Cross entropy loss works because cross entropy is something that you would have trained with, but any other kind of a loss function generally also works. And you'll be able to use the exact same framework. Again, nothing from both counterfactual cam and contrast cam is different. The way you get your alpha, the way you just multiply alpha given your convolution channels, and the way you use ReLU is all going to be exactly the same. What you're going to be backpropagating is different. Initially, you were backpropagating prediction for GradCam, the negative of prediction for counterfactual cam, and now you're backpropagating a loss function between some P and some Q for the output for the contrast cam. So the methods themselves are essentially the same. What is changing is basically this, what you're backpropagating. So this is where the idea of gradients are very important. Gradients can extract different things based on what you want out of it. It could either be a predicted value, prediction output, or it could be some kind of a loss function between two different things. And all of them are valid backpropagations, and you will get some results in these kind of backpropagations. So in this case, we have a couple of examples here. All of them most of them you have seen before, so I won't go through them. And most of them are also very human interpretable. So in this, at the bottom case, right? So I don't know if it's very visible. You have Stanford cars data set, and this image belongs to that of a Bugatti Veyron. So Bugatti convertible, sorry. So if you ask why Bugatti convertible, it's going to show you the important aspects. Now, if you ask why convertible rather than coupe, it needs to show you the top, which is the roof of this particular car. In this case, that is exactly what it shows. The roof of this car is different from the previous ones, from the Bugatti convertible. Hence, it is not a Bugatti coupe, rather it is a Bugatti convertible. Again, we are not utilizing the coupe image. So this is just shown to show you what a coupe looks like. But essentially, the network has knowledge about the coupe. And going back to the very first thing that I mentioned, which I'll bring back in a bit, it has knowledge about a coupe as well as a convertible, and we are able to extract it based on just this one image that you see here on the left-hand side. Now, all of these are kind of human interpretable. If I show you the next ones, oops. Okay, so in the there are some of them which are the same as GradCam. So in this particular case, given a representative Blue Jay image, and you ask the question, why Bull Mastiff rather than Blue Jay? The answer doesn't need to give you a very fine-grained difference, saying that, oh, the beak is different between the two things, because the beak does not exist in a dog, right? So every part of the dog that was used for GradCam is different between the Blue Jay and the dog. Hence, it's exactly the same thing, and you really don't need any other kind of an explanation in this particular case. Your contrast cam is going to be same as GradCam. There's some things that are not human interpretable. We talked about this stop sign image before. Let me actually remove the highlights. I'm not sure if it's very visible. So given this kind of a data set with only traffic signs, this is of a no left image. If you ask why no left image, the answer needs to be that there is this kind of a cross across the traffic sign. And that is what you see here. The cross is being highlighted. Now, if the question is why is this why no left rather than stop sign, as a human being, what I'm going to say is that there is no STOP in the no left sign. But a neural network, you can see, is looking at the bottom left corner of the image. And this is not something that is very intuitive. It is not looking at, I would have expected, again, the letters to have been highlighted within this particular image. I would have expected the output to look like STOP, since that is not there. That is the reason why it is not a stop sign. But unfortunately, that is not the case. And this is human and uninterpretable unless you know a few things about the network itself. Now, let's try to understand this particular data set. The data set was trained on these kind of traffic signs. There are a large number of traffic signs. In this case, I think it's about 14 different traffic signs that were used. What you notice very quickly is that the stop sign is the only one which has this kind of this octagonal structure. And the bottom left corner of the stop sign has this edge function. That is not there across any of the other images. Now, this is the only one with this octagonal structure with the bottom left. Hence, it makes sense that as soon as the network detects that that octagonal structure is not there, there's no straight line in the bottom left edge, that is sufficient for it to suggest that it is not a stop sign, rather it is some other sign, rather it has to be maybe in this case a no left sign. So the difference between the two things, the way we human beings do it, is not the same way that a network does it. A network is what you would call a very lazy machine. It'll try to find the difference between two classes in the easiest way possible. It doesn't have to align with human beings. Now, if you have heard of human aligned purpose, it's one instance of this human aligned purpose, where the idea is that a network or a machine has to work in a similar fashion as in a human being, but most of the times it does not, because the way it works is very, very, very compounded by how your data is structured. So it is not aligned. And by asking very simple questions, like why no left, you'll not be able to understand the purpose or this alignment. This here is the right explanation. this here, I would say, is not a human aligned explanation. I'm not going to make a statement saying it's right or wrong, but what I would say is that it's not a human aligned explanation. And that is where this idea of explainability and interpretability is very, very helpful to us. So I started off with this very, very important sentence that I mentioned before, that at the time, again, I had not motivated, but right now I think we have enough motivation to actually visually see what is happening. At inference, given a single image from a single class, we can extract information about other classes as well, right? So given the image of a cat, I told you before that I'll be able to understand something about a dog as well. So let's try to pass that particular statement. So on the left-hand side is a spoonbill that we have seen, we love, and it passes through a network. This network has already a lot of knowledge, has a lot of information stored within it. It's dependent on beak, neck, legs, feathers, water, grass, teeth. So in this case, the most important factors are the first four, which is the beak, neck, legs, and feathers. All of them kind of combine together in order to give me the output that it is a spoonbill. And that's what a visual explanation needs to show us. All these important factors have to be highlighted. Now, again, during inference, I have access to F and I have access to only this spoonbill image. But now when I ask the question of why spoonbill rather than flamingo, the output is going to show you the neck. So in essence, without giving the image of a flamingo, you're still able to extract the idea, the information that the difference between a spoonbill and flamingo is in the neck. Right? And this is what essentially we mean by visual information. It's not about this image and this class, but visual information gives you an understanding of the parameters of the network that is being used to show the difference between these two things. By backpropagating the loss function between a prediction and a contrast class, I'm able to extract this kind of information that exists in within the network. Again, we are not showing it an image of flamingo during inference. We're just showing that of a spoonbill. But I can ask thousands of these questions. Why spoonbill rather than flamingo? Why spoonbill rather than crane? Why spoonbill rather than dash? And so on. And I'll be able to get information about all these things. And this is what visual information is. And this is how I'll be able to extract this kind of information. And that is why I mentioned at the beginning that sentence, where given a single image, a single class, I'll still be able to understand or extract information about all of the classes. It exists because of this idea. It explains all the other classes as well, if we ask the right questions, which in this case is YP rather than Q. Yes. That's a very important and good question. Yes, it will be part of the training data because the network needs to have that information stored within it. Only when the information is stored, you'll be able to extract this kind of information using gradients. Yes. So the next question, so as an output for this, sorry, I don't know how to remove this. All right, so as an output for this, what we want is a case study. How do we use this all information? Now we know that all this information exists. At inference, we can extract it. How do we utilize it in order to make a better network? We want to make a more robust network. And this is where this idea of introspective learning comes in. Again, this is more of a case study of what we just talked about. This was a paper about 2 years ago at NeurIPS. The idea was about introspective learning and a two-stage approach to inference. So I'll bring the slide back, which is given this image. There's a reason I showed this image, right? The goal was for you to actually look at it and introspect within yourselves. And you probably ask your questions, why you were showing this slide and why you were showing these particular images. If I had shown you, instead of this breed of dog, if I had shown you something like a boxer or a bull mastiff, it would be very apparent. It would be very clear why these two things are different. So the reason was that I wanted you to know that that you yourself would introspect, take a couple of seconds, and after those couple of seconds is when you would decide that, oh, this is a dog and this is a blueberry muffin. So essentially what you have done is introspect within yourself. And from psychology studies, there's decision making is not a feed forward one step process. There is a sensing aspect to it, of course. We sense visually what is happening, and then we reflect within ourselves. We see a particular image and we get a certain output in our mind. We think, oh, this is a spoonbill. And then we start second guessing ourselves. We'll ask ourselves, why spoonbill rather than flamingo? Why crane? And so on. And we will then use the information that we asked ourselves in order to make a better and more well-informed decision. So that is essentially what introspection is, or at least the goal of introspection is. And the output of such introspection is that the output that we have, the decision that we make, is generally more robust. It is better than otherwise what we would have as our outputs. So the goal for this particular case study for the next about 5-10 minutes, I would say, is to actually make this kind of an introspection within a network process. So in this particular case, our goal is to simulate this introspection in neural networks. And we define introspection as some answers to these logical questions, right? So now the question is, what is that question? It's not very straightforward to us because, again, introspection comes from a psychology literature. And to now combine that psychology with these 1.76 trillion parameters is not going to be simple. So we have to have a very clear definition, goal, and more of a technical definition for what this introspection is. So what are the possible targeted questions we can use for introspection? The good thing is we already talked about 3 of them. We talked about questions that are YP. We talked about questions that are what if, and then we talked about questions which are YP rather than Q. So this contrastive, counterfactual, and correlation questions are the logical questions that we can use within an introspection framework. So instead of just saying that it is the answers to some logical questions, now I have a more contrastive definition of what introspection is, which is that they are answers to this kind of a YP rather than Q, a contrastive question. And the technical definition is that, again, we have talked about gradients until this point. So gradients are the thing that were the defined the features, right? They are the alpha parameters that multiplied the convolution in order to get our results. So the technical definition of introspection is going to be the given a network F and some data point X. Introspection is the measurement of change within the parameters that is required in order to move to the next class. So given this kind of a Q class, there is some change that needs to happen within the network, and that is what you're reflecting. That is the introspection. The change, the magnitude of that change within the network which is required is the network introspecting and telling itself that, oh, if this is not a spoonbill, then it has to be a flamingo. And this is the change that I need to do within myself. My parameters have to change in order to make this new decision, new contrastive decision, that it's a Q, that it's a flamingo, rather than a spoonbill. So that is what we mean by this kind of a technical definition of introspection. And I'm just showcasing the gradients here in the final fully connected layer. On a very simple MNIST data set, this is what 5 looks like. The network is, again, very good. It tells you it's a 5, but then you're not very sure because it kind of could be something else. It might be a 6 as well because of the fact that, these two are connected. So when you actually go through the gradients themselves and ask why 5 rather than 0. I'm not doing a visual explanation here. I'm not doing the GradCam alpha. I'm literally just showcasing the last fully connected layer in a neural network. A last fully connected layer in a neural network has this kind of since there are 10 classes in MNIST, this particular neural network, you see on the y-axis, there's about 10. And then the x-axis is basically the dimensionality of your final fully connected layer. So in this case, it's about 50 cross 10, which is, again, not as important. What is important is where the logics requires changes. So when I ask why 5 rather than 0, the things that need to change is, it needs to change the weights, the parameters in the 5th filter, and it needs to change in the 0th filter. So it needs to become closer to the data point. The 0th filter has to become closer to the data point, while in this case, the 5th filter has to become closer to the data point. So that is what you see, Wi-Fi rather than 0 here, and Wi-Fi rather than 1. You'll have the blue dots here on the top at the first point. So Wi-Fi rather than 2, you have at the second filter. Hopefully that part is clear. So the goal of this is to show that these gradients, they are sparse and informative features that help us in order to quantify the required change within the network parameters. Of course, there's a little bit more technical details in terms of the theoretical way of calculation of gradients. Gradients are very good because not only does it show us the change required in this case, phi, but it also shows us the change in zero. So mathematically, if you look at the formula itself, if you add some kind of a noise within the network, within the data point, sorry, then not only does it need to change the filter for 5 to make a wrong classification, you also need to change the relationship between 5 and 0. You also need to change the relationship between 5 and 1. And this requires more amount of noise in order to change all the 10 different relationships. And if it's imaginary data set, then it's 1,000 different relationships. So if you're using gradients of features, it is more robust compared to you are just using your activations. That's the goal of this slide, which is that this relationship between classes is something that we need to use within in order to make a more robust decision. The methodology of obtaining these gradient features, very straightforward. Again, we're only looking at the final fully connected layer. This is similar to when we use GradCam. It really doesn't matter what kind of an architecture there is. You just have the outputs. You can backpropagate it. Everything has a final layer. Every architecture has access to gradients because you would have used backpropagation for training, and you use those gradients instead of backpropagating. In this particular case, I was showing 1 0 0 0. This is when q equals 1. Q equals 0. Then 0 1, all zeros. This is when q equals 1, and so on. There is a way that if you're using just the final fully connected layer, doing those different number of backpropagations is the same as just backpropagating once in terms of just one vector of all ones, and you'll get what your output is going to be. So it's basically going to be something of a confounding label. And once you have that, you can extract the gradients and all these. Again, I'm not using any novel data at all. I'm just using just the training set. I can just take and get an MLP, like a very simple 3-layer perceptron. And right now, instead of X being these pixels of an image, it's nothing more than the gradients from the final output layer. So each X1 is Rx1, which is my gradients of input image 1. Rx2 is a gradient of input image 2, and so on. I can train a very simple MLP, and the output of it is going to be more robust than without it. So when this introspection is useful, you can do this on normal data itself, like the training distribution data itself, and on the test distribution. But you won't observe any performance enhancement when you're looking at the same train and test distribution. Introspection is useful in the case when there is some kind of a challenge, sometimes some kind of a novel data during test time. And again, even psychologically, this makes sense. You don't always introspect on very simple things. If I had shown you the difference between a boxer and a blueberry muffin, you really wouldn't have required more than 80 milliseconds. That's the perception time it takes in order to say that this one is blueberry muffin and another is a dog, but a boxer. But since I showed you a breed of a dog, which is very similar to that of blueberry muffin, you take a couple of seconds, and this is where the reflection part comes in. Generalization ability is dependent on how good it works on novel data, and this is where introspection helps. So it helps us for increased accuracy on, when I say OOD, it's out of distribution data, and calibration, it reduces the difference between prediction accuracy and some kind of a confidence measure that might exist. So if you have not heard of calibration before, it's this application area where ideally, before in the 90s when we had small neural networks, the confidence and your accuracy always was together. So that is what you would have seen on the left-hand side here. If my confidence was 0.4, on, let's say, 100 different images, about 40 of those would have been correctly classified because 0.4 is the confidence, 40% would be the accuracy. So if you plot your accuracy on the y-axis and confidence on the x-axis, you'll generally see that it's a 45-degree line. But what has happened recently with these large architectures is that most of your network is very, very confident. It's more confident that even though the network might be incorrect, it's very, very confident. That's why you see this kind of, even though the error is lesser, before the error used to be 45, now it's 30, it doesn't matter. At the very end, most of your confidence is between 0.9 and 1. So even though it's incorrect, it's very confident that it is correct, which is problematic in during a decision phase when you're deploying it and you want users to use it, right? So ideally, you want this gap between red and blue to be less, like it is on the left hand side. But unfortunately, it's usually like what you see on the right hand side over here, where there is a large gap. And the difference between the two is called the calibration error or the expected calibration error. The mean of all of them is the expected calibration error. What we see when you do introspection is that if I plot the expected calibration error on the x-axis, the performance accuracy on the y-axis, all networks move towards the top left. That is, they'll have a higher accuracy and they'll have lower expected calibration output. Again, this is not based on the original test set. This is based on some corrupted version of the test set. So in this case, I believe CIFAR 10C takes all the data from the test set of a CIFAR 10, which is about 10,000, and adds about 19 different distortions onto it at 5 different levels. So at the end of the day, each of these networks is tested on about 950,000 different images. And based on that, the average values usually see that it moves to the top left corner, which means that it is more accurate with less calibration error. The good thing about introspection is that it's something that you can put on top of any kind of training that you want. A simple ResNet 18 training methodology from 67%, your introspection increases to 71%. But there are other methods of training, right? So during training, you can include your novel data. If you have adversarial training, if you have SimCLR, if you augment noise, your original data output increases, original sensing network increases, but introspection increases even further. From 70, it becomes 73, 76, it becomes 77, 89.85, it kind of remains 89.89. But what I don't have in this table is the expected calibration error. That decreases by more than 43% for the augments. So essentially, it's making any network more robust, which is ideally that we want in this kind of example. So this kind of introspection is a plugin network. It can work on any other application. So it just makes more sense to talk about, or it is easier to talk about image classification. But if you're interested in image quality assessment, if you're interested in out of distribution detection, if you're interested in active learning, in all these cases, introspection helps, because first off, in image quality assessment, what you try to do is predict the quality of a distorted image. So you would have trained with normal data and you're testing with distorted data. So again, this is where introspection helps. In out of distribution detection as well, you would have trained with normal data, and while testing, you have a combination of normal and out of distribution. This is where introspection helps. Active learning is kind of the different case where your network is not trained well. Even though your data is normal, your network is not trained well in the initial stages, right? It does only have access to a very small subset of images. So as and when you increase the data, your network becomes better and better. So you can think of it as noise in the network rather than noise in the image. And in those cases as well, introspection essentially helps. So anytime you would require this kind of a generalization ability, that is when you would take these gradients. You would use the fact that gradients have access to all the relationship information, and you use that relationship information as your feature, and you'll get a more robust decision based on it. So that is the end of part 2, which is explainability. So the next part is going to be about uncertainty. I think we can take a small break here of about 15 minutes. I think it's been about an hour and 15 minutes for the first 2 parts. The next 2 parts, again, are very similar, about 30 minutes and 45 minutes. And conclusion won't be more than 10 minutes. So that basically means that we have about another 1 hour 15 minutes to 1 hour 30 minutes. So it's about 3:17. So we can restart again at 3:30. So if you want to stretch your legs, have a little bit of coffee, which I'll try to do myself, it'll be a good thing to do that now. Thank you. Oh, thank you. All right. So, at least for me, that was a much needed 15-minute break. Uh, Hopefully, my voice is better now. It's stronger than it was before. I had a cup of coffee as well as an entire bottle of water. So, let's start with part number three. Just to recap, we have done two parts. Just an introduction into the idea of inference, and what are the required parts of inference that we are interested in, which is the gradients, followed by explainability and how it helps inference to make it more robust. So now let's talk about the idea of uncertainty. And specifically, we'll discuss about four topics, which is definition of uncertainty, what uncertainty, how can we quantify uncertainty, followed by more relevant things for us, which we have talked about till now, which is gradient-based uncertainty and some kind of robustness measures that we can perform with the help of this gradient-based uncertainty. Now, the reason we'll have about 4 slides that talk about the definition of uncertainty is because the word uncertainty is a very colloquial term that we use in English. Every one of us probably uses that word on a daily basis. Whenever you don't know something, you might just say that I'm uncertain. Now, there are some good things and bad things associated with that phrasing, which is that since the word uncertainty is colloquial, it's not very clear how that translates to something like machine learning, because uncertainty, trustworthiness, prior belief, all of them kind of mush together sometimes, and it's very hard for us to differentiate it. So we'll spend about 4 slides today just trying to define what this uncertainty is. If you read papers, one thing that you generally see at the beginning of the abstract is that uncertainty for a particular model is that model knowing that it does not know. And let's start off by just looking at this particular dress. I have always looked at the left two images, and I always think it's a white and gold dress. Now, a few years back, this is something that took the internet by storm. Many of you would look at that and say that it's blue and black, whilst many of you would look at that and say it's white and gold. For me, I've always looked at this and I've always thought it's a white and gold dress, but only when I see the right-hand side image do I look at this and think that, oh, it's actually red and blue. Even after I've looked at the right-hand side image of the black and blue, I still cannot see black and blue on the left-hand side. I still always see white and gold. So this calls into question, can you trust your own perception? What is the uncertainty related with your own perception? So I need to understand that my perceptual model doesn't know, or you cannot always know essentially or trust your perception model. I need to know that I don't know these particular colors essentially. Another way of thinking about uncertainty is from a data perspective. You look at this between, let's say, minus 0.5 and 0.5, and you think it's a sinusoid, right? You look at this kind of a shape. It goes from 1 to -1, from between minus 0.5. It's kind of has the symmetric ability and everything. So it looks very much like a cosine signal. But you're only given between minus 0.5, 0.5, and 0.5, or data between minus 0.5 and 0.5, which is the small pluses that you see here. If you use a regression model to train this, it will not understand that this is a sinusoid, that it is a part of a spline of a sinusoid. Rather, it assumes that this kind of goes up on top and this kind of goes to the bottom. So your network will always predict based on the red line that you see here, which is a predictive mean, but it needs to understand that it is uncertain about these regions. And that is where the variance comes in. The variance across that mean would be the uncertainty in this case, and the network needs to know that anytime it is predicting in a region that is outside of minus 0.5 and 0.5, it should not be very confident of its prediction. There has to be a certain uncertainty associated with it. A very simple way of defining uncertainty in this example is that when you have data in a certain region, then the network has to be certain there. When you don't have data in a certain region and the network is trying to interpolate that particular data, it has to be uncertain. Again, this is a very simple example, but this occurs in normal day-to-day life as well. When you use ChatGPT, you can be very sure that most of the things that you're asking ChatGPT, it should be very uncertain about it. Because if you're asking it to construct a city in Venus with, I don't know, like marble or something like that, it's not something that it would have seen during training. Right. So it is something that it has to be uncertain about, and all its output needs to be uncertain in that particular fashion. A more mathematical way of thinking about uncertainty is by sources of uncertainty. Again, the word uncertainty is very colloquial in English, so it's really hard for us to use the same word in multiple machine learning terminologies. So the way we then think about uncertainty is based on the source of what that uncertainty is. A source of uncertainty can be either model or the data. In the previous one, it was about the data, but sometimes it could be the model as well. Let's say I have a very simple sinusoid. In this particular case, I have the sinusoid with a certain known frequency. Unfortunately, the way I have measured this frequency, it may have been incorrect. And that's why initially I have the my model, which is given here with black and then red. In fact, I only cannot make out which is red and which is black here. So I'm just going to expand it a little bit. So the one on the red is the frequency with noise and black is frequency without noise. So I've used a model essentially to kind of construct or reconstruct the signal, but unfortunately there was certain noise associated with it, which I did not know beforehand. And hence, as you progress from the 0th sample onwards, your uncertainty needs to increase, that all these regions there, you're not very sure of where you would have to reconstruct. This is what is called data uncertainty, or what you would normally call as aleatoric uncertainty. There is another kind of uncertainty, which is model or epistemic uncertainty. So in this particular case, let's say my original signal had a phase associated with it. But unfortunately, I didn't know that beforehand, and I did not account for it in my model. I just used a cos 2 pi ft as my original model, and I tried to now reconstruct a signal, which in fact has a cos 2 pi ft plus a certain phase phi. Since the model I've used cannot account for this additional phase, all your outputs will now have certain uncertainty associated with it. So this is what is called model or epistemic uncertainty. Now I'm explaining this in terms of sinusoids, which makes it easier. But from the perspective of these deep networks, you should have used an architecture which was, let's say, a ResNet 151, but you chose to use an architecture which is, let's say, ResNet 18. So this is where the discrepancy comes in. The model with phase and without phase. You have used a model which is ResNet 18, which is the black model, but then ideally you should have used a ResNet 151. And this is something that you would have used during the training phase and now deployed it. This is the uncertainty that exists because of your chosen model. This is where the aleatoric uncertainty, epistemic uncertainty. If I talk about aleatoric uncertainty from the machine learning perspective, you have only used data sources which are pristine. You have not used novel data sources, or you have not used rainy data sources, let's say, just going back from the initial example. So the uncertainty is now kind of broken down into these two things, which is aleatoric and epistemic, depending on the source from which it might come in. So this is like a simple way of looking at the sources of those uncertainty. And generally, we are very, very interested in where a network is uncertain. Now, this is a very segmentation model. So given an input image, you have the neural network output. So anything in green is essentially a foliage, your trees. Anything in purple is the pavement or your roads. Anything in dark blue is your bus. Now you see that this bus here does not follow the shape that you think it should. That's because in this region, it's giving you an output, which it's trained to do, but it's not certain of this particular output. Hence, you need an uncertainty heat map. And in this heat map, it has to be high. So anything that is blue in the uncertainty heat map means that the network is quite confident, or it's quite certain of its predictions. But as soon as you come to the right-hand side on the front part of the bus, it's not very confident. And your network needs to know that what it has predicted is not always confident. Again, this might be because of aleatoric, it might be because of epistemic, but there has to be a level of, or a certain uncertainty that is attached to a network's prediction. And that is where the uncertainty comes from. So this is like the definition of uncertainty. It's basically, uncertainty is a model knowing that it does not know. The top sentence applies, but making it more formal or more mathematical is a little bit more difficult, because we are moving from a colloquial phrase now to a more machine learning related mathematical phrase. So what does that mean from the perspective of a neural network? This kind of uncertainty quantification is very, very challenging to neural networks, right? Because generally what happens is that the primary purpose of a neural network is in conflict with your uncertainty estimation. That is a very important statement that I'm making. I want to motivate that using these two examples here. Now, if my goal is image classification, output is very straightforward. Both of those images are dogs. But let's say that you are using a VLM or some kind of a language model that is associated with your visual model. You want to know that this dog is just sitting up straight, it's kind of angry, versus the same breed of dog is asking for some kind of belly rubs, right? So these are two different dogs. These are two different moods of dogs, and yet they both are the same classification of a dog. So if your goal is just simple image classification, uh, any attributes that are associated with this dog are lost during the training process. And the uncertainty, which is these kind of attributes within the framework, is lost when your primary purpose is just a simple image classification. So in most cases, it doesn't matter what case, anytime you have a supervised learning algorithm, or even within generative modeling, when you are finally using that to infer something, you are losing your initial uncertainty so that you can perform your primary purpose better. Anytime you have a very good classification algorithm, you would have lost a lot of attributes from this perspective. To make it a little bit clearer, let's see it in terms of graphs. So this here is a very good neural network output. So you see that all dogs basically are, let's say, triangles. So they come and they regularize themselves within a very small cluster, and you'll be able to classify this cluster away from this cluster quite easily. But you have lost a lot of attributes within this cluster, right? These two dogs are very different looking, and yet in the representation space, they're very close to each other. If you want to keep the attributes separate, then this is how the representation space is going to look like. Yes, the dogs are probably in the left-hand side, and yet there's a large of intra-class distance. So not only are we considering the inter-class distance, which in this case is quite high, which is the primary purpose, but the intra-class difference, which is the difference between the mean, let's say, and all the parts of the points within the cluster, also needs to be high in order to create these kind of uncertainty metrics. This metric, this point here, let's say my mean is somewhere in the middle. This data point is quite far away from it, right? So it has more uncertainty as compared to the mean dog that you would have seen. Unfortunately, our general purpose, primary purpose of neural network, whenever we are using supervised training, essentially does this here on the left-hand side. You're trying to make sure that the interclass distance is very high. You don't really care as much about the intra-class distance. That is what is called as preservation. You're trying to preserve features. And there's no preservation, something like this happens. And if feature preservation is there, something like this happens. And unfortunately, we never try to do feature preservation because performance declines. And this is a huge problem within uncertainty literature. If you're going on a little bit of detour, if the uncertainty that you have heard of is from Heisenberg's uncertainty principle, it's still a very similar principle here. So ideally, when you measure something, let's say the position with respect to its velocity, if you measure the velocity, you have changed the position. If you're measuring the position, you have changed a particular velocity. So by making sure that you can do uncertainty well, your performance has declined. But if you're doing performance, then your uncertainty estimation is going to decline. So there is this trade-off between accuracy and uncertainty that is very, very important within this kind of frameworks. So keeping that to the side, that is where the inference aspect comes into picture. We don't want to change anything within the network during training. What do we change during testing is what we'll be discussing today. The simplest way of doing this kind of uncertainty quantification is something called ensemble networks, which is you train 50 different models to start with. So you have, let's say, 1 million data points. You usually train a single network, you get the logics, and you get your outputs. But if you had the capacity, the hardware and the software capacity to train, let's say, 50 different networks, you can see the difference or the change in the logics, some kind of variance in the logics or entropy in order to create the uncertainty metric. So from the first F1 of theta, you can see that the cat the level of the cat changes, the level of the dog changes. So in the first one, it's probably cat is 0.8 versus dog is 0.15. In the second one, cat is 0.7, the dog is 0.3, right? I'm talking about the confidence. So 20% in the first one, 30% in the next one, 10% in the next one. So maybe if you now take an entropy across all the 50 different architectures or variants, you'll be able to get a measure which is your uncertainty. And this is generally agreed to be one of the better ways of estimating uncertainty in these kind of deep neural networks. Again, before the 2000s and 90s, there was a lot of works in uncertainty quantification, most of which may not readily apply to deep neural networks. And that's why ensembles is considered one of the best ways of estimating this kind of uncertainty on large data sets. But I think now it's pretty straightforward that this is not something that is possible in most cases. Generally, we don't have the luxury to define 50 different models, right? The amount of money it takes these days for the large models, if you're using AWS or something, or Microsoft Azure, in order to construct these models is very large. And also the inference time as well. In some safety critical applications, you cannot wait to get outputs from 50 different models to get your uncertainty quantification. Hence, it's not the most preferred methodology of doing it. And there are different approximations to this uncertainty measurement. The most common of which is something called Monte Carlo dropout, or MC dropout. This is something that you might have heard while training. MC dropout is one of the better regularization techniques during training. The way it works is that you take a particular cat, you pass it through the network, and you're assuming that the network was drawn from a Bayesian distribution, which implies that each of the weights is in fact based on a distribution. There's a mean associated with it, and there's a variance associated with it. And this goes back to the epistemic uncertainty, right? We talked about how maybe there's something with phase or without phase. In other words, maybe there was a different architecture that would have given you a better result, or there was a different parameter that would have given you a better result. And the Bayesian neural network accounts for it. Essentially, that a different parameter, in this particular case, let's say the parameter was 0.2, if it were 0.3, it would have been better. And that is what a Bayesian neural network does. So we try to approximate that Bayesian neural network using MC dropout. Monte Carlo dropout, the way you do it is you define a particular number, a probability, let's say 0.2. And that 0.2 means that at inference, at one pass of an inference, 20% of your parameters are made zero. Or you're not going to be using 20% of your activations during inference. So think about that fully densely connected network we saw before, and think that 20% of those activations will not be used. It'll be zeros. And essentially, the output will be dependent on the next 80%. You might get an incorrect prediction, which is possible for sure. And that's why we have T different forward passes. In other words, we can have 50 different forward passes on the same network. So technically, what is happening is that you're approximating this kind of 50 different networks by zeroing out certain parameters, random parameters, 50 different times when you're forward propagating it through the network, which implies that you will get, again, T different logits, and you can use that in order to calculate entropy of variance, which is exactly what you did before as well, right? You ideally had one logit, two logit, and n different logit, and then an entropy of variance in order to get uncertainty quantification, which is exactly what you do here as well. Getting these T different logits, now you make some kind of an estimation on it, and that estimation is given by this methodology here. So FW cap T of X is your output logits. And there's two kinds of uncertainties. One is aleatoric and epistemic. What you find here is aleatoric. Maybe this would have been easier if I had put it on the left-hand side. So generally, aleatoric plus epistemic is your predictive uncertainty. So the predictive uncertainty is the one that is in the middle. On the right-hand side is aleatoric. You see a negative sign. Think of this as something that comes to the LHS, your left-hand side. So your aleatoric plus epistemic is going to give you your predictive uncertainty. Now, this might appear like a difficult equation, but essentially it's like the entropy of logits, entropy of mean of logits, versus the mean of entropy of logits. That's the main difference between the two things. Exact formulation is not as important, at least for this particular tutorial. It's just showing you that given these different set of logits, you can combine them based on entropy if you're taking individual logits, or if you sum them up or mean them up and then take the entropy, you'll get a different kind of estimation. You'll get either predictive uncertainty or you'll get the aleatoric uncertainty. Now, this seems like a very simple way of constructing your uncertainty scope, but it's not always the case. This kind of uncertainty estimation suffers from the fact that the dropout, which I said 0.2, is something that is decided initially during the training phase itself. And generally, dropout is utilized for regularization. And that dropout percentage may not be something that would be required during inference. So if you use 0.2 while training, you have to use 0.2 while inference as well. And for some modalities, which is not natural images, like something like radar or LiDAR, those numbers are not sufficient. So if you're using other models like transformers, for instance, whose accuracy is very high, generally they're very robust to begin with on the training distribution. So when you're using dropout, you won't get a difference, much difference in your logics. So when you take the entropy, the result is not going to be as good. So MC dropout works well with some kind of initial networks, let's say AlexNet, but it kind of fails as you come to the more bigger networks, neural networks that can exist. Or it kind of works on natural images, but if you're looking at LiDAR or other kind of images, it doesn't work as well. So that's the issue with this kind of MC dropout, but still it's a good approximation for the ensemble networks. So this is where the single pass uncertainty estimation comes into picture. Now we started off by talking about that intra-class distance, right? So this is where we'll be using that intra-class distance in order to make the assertion that something is uncertain or is not uncertain. So given this kind of a simple manifold, and then given novel data, if you're able to calculate some kind of a distance between that manifold and the novel data, that can be considered as an approximation of your uncertainty. There are methods. I think this method is called DUQ that does something like this. What they do is they construct or they require this kind of a validation set of images or a training set of images. And based on that training or validation set, there is a Gaussian process involved, and you calculate the distance from that Gaussian process using this methodology. The issue there is that during inference, we don't have access to those kind of training or validation set. It makes sense if you are in a laboratory setting, but as soon as you come during deployment, that you don't have access to such data. This is where you only have access to a single data point, and your other parts of your network is kind of grayed out in this particular case. We have seen this kind of image before. The reason I'm showing this back right now is that we'll be using gradients in order to construct this kind of distance. Now, we know already that gradients give you a local information. We also know that by backpropagating these kind of contrast or wrong gradients, we'll be able to get some information about different classes. We'll be using that aspect in order to construct these kind of uncertainty distances. Now, this particular image we haven't seen. We have only seen local information, the red being there. This is where we are constructing the counterfactual, the contrastive gradients. We saw contrastive explanations, right? When you backpropagate the loss between J and Q, what essentially was happening is that you were seeing the amount of change required in theta naught and theta 1, that is different parameters within the network, that would allow you to now construct a wrong prediction, in this case Q. So X now becomes X dash, or it moves the module, your entire manifold towards a different spot. You're not able to reconstruct the manifold, but now you're constructing a different manifold, and you're looking at the change from the different manifold to an unknown manifold, essentially. That is what gradients is giving you. So the problem, of course, in utilizing gradients is that we need some kind of a loss function, and we backpropagate that loss function. It's very straightforward in training, but during test time, we don't have access to that. So we go back to the methodology that we were discussing before with explanations, which is that we are going to backpropagate the contrast classes. So given a spoonbill, we will backpropagate, let's say, a crane, a flamingo, and so on. Very similar to the introspective learning thing that we did before. So essentially what you have is given Q1, let's say, which is a flamingo, it now has a different manifold. Given Q2, it now has another manifold. Of course, it could be in different directions. It's just that it was easier to construct these kind of images where I was able to do it on PowerPoint itself rather than having to generate. That's why you see that it's just one on top of the other. But essentially, it could be in any direction that you want. So we can backpropagate all these kind of contrast classes and get some gradient measurement with respect to these results. Again, this is another slide we had seen before, which is that we'll be able to backpropagate a vector of all ones and extract the gradients for all these contrast classes in a single backpropagation step rather than doing it a large number of times. So instead of just putting it into the network, this stage, I just want to show you what the aggregate of gradients look like. So let's say this is for a VGG16 architecture, and a VGG16 architecture has a large number of layers. There's convolution, there's batch norm, there is some kind of a max pooling. And across all these layers, there's going to be some gradients for the learnable parameters, not for the max pooling. For all the other layers, there's going to be learnable parameters, and you'll get gradients for all those particular parameters. And if you take the energy of these gradients, which is nothing more than a collection of squared L2 norm, this is the difference between something which is out of distribution in orange and something that is going to be in distribution. So on the right-hand side, you see that the in distribution is, I don't know if it's visible. So the in distribution is, we'll be using MNIST, and the out of distribution is going to be like an LSUN dataset. So what you notice is that the gradients of LSUN dataset is generally higher compared to that of the out of distribution gradients, which is LSUN, is going to be generally higher than your in distribution gradients across different layers. It kind of changes in the final fully connected layer, but across initial layers, it is all going to be out of distribution will have higher gradients. And intuitively, it makes sense. The amount of change required to include a data point, which is completely out of distribution, needs to be higher. More change is required in your parameter space in order to construct that new image, which is going to give you a different answer, right? So we're going to make use of this fact that there is a large difference between the gradients between the in distribution and out of distribution, and construct a method around it, basically. So before, what we saw was layer by layer, but if you aggregate across different layers, this is what you see. So if MNIST dataset is in distribution, generally you see that this dataset is always at the bottom over here. And as and when you look at different out of distribution datasets, their gradients, the output of their gradients is going to be much higher. So this is a box and whisker plot. Mean is given by something here, while the whiskers are give you the variance across the different images. There is, of course, 10,000 different images, let's say on something like MNIST on SVHN. So across the 10,000 images, this is how the magnitude of the gradients, the L2 norm of the gradients is going to look like. And hopefully it's clear that there is a difference between your gradients in distribution and then out of distribution gradients across the different architectures. Now, again, we're going to be using this across adversarial, noisy, and OOD detection. So I'll directly jump into those kind of applications. Adversarial images, we started off with this, right? We started off with novel data sources. We talked about out of distribution. We talked about noisy characteristics, adversarial characteristics, and so on. Adversarial images are this special type of engineered images where instead of just randomly adding noise, which we saw during introspective learning, we are adding a very engineered kind of noise. We want to make sure that the network fails intentionally. So an architecture looks at this image and tells you with 57.7% confidence that it's a panda. It is a panda. We know this for sure because we can see it. But then if you add a very, very small amount of noise, it's imperceptible. And it looks like here on the right-hand side. If you pass the right-hand side image through the network predicts a gibbon with 99.3% confidence. So something that was correct on the left-hand side has now completely shifted on its head. It's a different classification, which is a given, and that too look at the confidence, 57% confidence for the correct one, but then 99.3% confidence for the incorrect classification. In this case, it is a given. So this noise is what is called an adversarial noise. It's a very engineered noise that we can add to any image for any network, and it's going to give you a completely incorrect result. Now, the exact reason for the existence of adversarial images are not known. We just know that since its neural networks operate in a very high dimensional space, there's a lot of wormholes that can exist in this high dimensional space between, let's say, Panda and a gibbon, where a small amount of imperceptible noise can move it across this particular wormhole. But the exact mathematical reasons of adversarial images are not known. In fact, there are so many methods of generation. Each generation, adversarial generation method is itself a reason for the existence of adversarial images. But our goal is to detect these adversaries. So at inference, we want to know if a given image is an adversarial image or if it's a pristine image that we had seen before. So let's say for the ResNet module, there's about 5 different ways of attacking. As I mentioned, there's not just a single way of creating these adversarial noise. FGSM was the first one, or I believe this was in 2014, this was like the first big paper that suggested methodology to construct these adversarial images. I believe there was one in 2013 as well, but that talked about the existence of adversarial images rather than having a method specifically designed for it. Then there are more iterative methods. PGD is probably the most well-known adversarial generation image generation, sorry. And based on all these images, you'll see that your baseline is generally around the 50-60% accuracy. That is, if you're given 5,000 images of adversaries and 5,000 images of normal data points, only in about 51% of the cases does a network see that it's an adversary or not an adversary, which means it's just a chance, right? It's just a binary classification at this point. It's a binary detection, sorry, which is it an adversary? It is not an adversary. So this 50% is very, very concerning. There are different methods. LID, M is Mahalanobis distance. So most of these methods, they do very well in terms of trying to detect or not detect your adversaries. So do gradients. So the R's here is actually gradients. So it gives you a good methodology of detecting whether something is adversary or not, based on that fact that we mentioned before, which is how much change is required when you're backpropagating the wrong classes and you take some kind of an L2 distance across it. Same thing with dense net architectures as well. It's able to do that. The good thing about these kind of gradient methodologies is that it's not just there for a specific purpose for adversarial image generation. So we saw during introspective learning that we use the gradients. We're using very similar gradients in this particular case as well for adversarial detection. You can use the same methodology again for out of distribution detection or corruption detection. So Cypher10C is what we were showing for the introspective learning, which was given a normal image. You just then distort it using, let's say, Gaussian noise or defocus blur, and there's 19 different types of distortion. If your goal is not recognition, but detecting that there is some kind of a corruption that is there, then basically this is uncertainty in detecting these challenging conditions, or in some cases we say it's detecting corruptions within your images. So we can see it either in Cypher10C or Cure TSR, and there's a lot of numbers here. Let me try to So let me explain what the table is showing you. The left-hand side, the leftmost side is the dataset, Cypher10C or Cure TSR. The next column is the type of corruption that exists. It could be some kind of defocus blur, some other kind of blurs, and so on. Levels here indicates the amount of distortion. This is very important when we discuss corruption detection or recognition as well. Generally, level 1 means that there's not as much noise that is added to the data. Level 5 indicates there's a lot of noise that is added to the data. Whenever you see these kind of tables, I'm not going to go through the exact numbers in the tables, but it's very important to recognize that it is easier to detect level 5 results than in something like level 1 results. That's because level 5 results mean that there's a lot more distortion, which means that it's easily perceptible. It's more perceptible to us as well, that there is some kind of distortions. When you look at level 1 data, even for me, sometimes it's hard to say if something is blurred or if this is how the original data looks like. In Cypher-10C, generally, you don't see that much of an increase. Everything is pretty high. You can easily say if something is distorted or not. But in more realistic conditions of these kind of traffic signs, you see that there is a difference between level 1 and level 5. In level 5, you generally see everything in 80s and 90s. But in level 1, it kind of decreases to 25, 70 to 50, and so on, right? So these are not numbers that ideally you want to see, especially in real life settings. So in these cases, there's still a lot of work to be done, essentially, in this kind of robustness results. But gradient-based methods do better, especially in the level 5. But in level 1, it's still 50, which is basically just it basically doesn't know if it's corrupted or not corrupted. 72, 83, of course, these are a little bit better, of course, but still, it's not as good as it could be. Which basically means that there is a lot of scope, essentially, in what we are discussing for future research directions. So that was about corruption detection. Now, if we go towards out of distribution detection, which is basically given a train set, our test set needs to come from a similar data set. So if your train set is MNIST data, and your test set is coming from something like SVHN, Cypher-10, Tiny ImageNet, or LSAN datasets, you want to detect the fact that this is something that you have not trained on, right? It's, again, going back, uncertainty is essentially a model knowing that it does not know. So it can make a certain decision, given MNIST dataset, it can decide on SVHN, but it needs to know that it has not seen this before. So it needs to give you an indication whether it's something that, hey, I've not seen this before. So take my result with a grain of salt. This is especially important when we are discussing something like healthcare settings. So even in these cases as well, gradients are generally helpful. There are, again, different methodologies. Now, the reason that we are showing all these different applications is that we are using the same method for adversarial detection, corruption detection, and out of distribution. There are many cases where some methods are going to outperform gradients, but still, the same method being placed across different applications has some value attached to it. So the key, again, is not the numbers themselves, but the fact that gradients can be used across all these applications to give you some kind of a good result. So I can also show the results for different things as well. So previously, what we were showing is in distribution Cypher-10, SVHN. What you notice in the SVHN architecture is that it's very good. The results when you train with something like SVHN and you test with something like Cypher-10, Tiny ImageNet, and LSAN dataset is going to work very well. But the opposite case might not be true. If you're training something with ImageNet dataset, you will expect that it has already seen features for something like MNIST dataset or SVHN. So the difference in the gradients is not going to be as high as what we showed you before, which is that, MNIST dataset versus something like SVHN and so on. So you have to do a little bit more engineering in those particular cases than in more simpler cases. Yeah, so this is essentially, so more similar dataset objects within Tiny ImageNet and Cypher-10. They, both of them will have a better correspondence between in distribution and out of distribution compared to something like LSAN and SVHN images. So that brings us to the end of uncertainty, which was part 3. And now we come more towards the next part, which is the intervenability. I just had a sip of water. Personally, this is my favorite part because everything that we showed before is something that we worked on 2 years before, 1 year before. But since then, this is something that we have worked on more recently. And the idea of intervenability is not as explored, let's say, as something like explainability or uncertainty. Because these days, with the advent of foundation models, if you have not heard of the definition of foundation models, it's basically these very, very large architectures that have been trained in a self-supervised fashion and can now be applied to any tasks. Most of these foundation models allow interaction with human beings. And it can be good or bad. It can be good because you can go to ChatGPT, you can ask it questions and get results. But the researchers who have trained this model would not have anticipated the kind of questions you might ask. And this is where the fairness and bias questions can come into the picture. So you want to make sure that when you're intervening within a trained model, it does not go beyond the operational limits that was trained initially. So that is what we mean by intervenability in this particular case. So there's going to be a lot of talk about prompting and how we use in this particular setting. But to make sure that we are not moving too far away from what we talked about till now, the case study we look at is more related to two things, which is explainability, uncertainty, and how we can use explainability as an application and uncertainty as a mathematical framework in order to analyze intervenability. In fact, the first part of intervenability is just going to be about definitions. As I said, the idea of intervenability is not very well known, or it's not as well defined. So in this case, we're going to be defining intervenability based on different aspects: causality, privacy, interpretability, prompting, benchmarking, and so on. And then we'll discuss some mathematical functions for what these kind of intervenability, how we can analyze them and have a case study within interpretability. All right, so this, if you have heard of interventions, most probably it is coming from the causality literature. We want to assess some kind of causal factors that might exist. Now, if we are dealing with something like tabular data and graph neural networks, it's pretty straightforward on how we can do, actually, I shouldn't say pretty straightforward, but it's a bit more easier and intuitive to think about causality in neural networks. But when we are discussing other kind of architectures and multimodal data, your text, language, your speech or images, it's very hard to differentiate between what those factors are. And we'll talk about that in a little bit. But essentially, one, through the causal glass, this is how you would define your interventions. More recently, there has been a lot of work that has gone on in the idea of privacy. If you've heard of the big topic of machine unlearning, it's basically you have a learned network, and then someone comes in and says, hey, I don't want my data to be part of your training set. In that case, you can, of course, the simplest thing you can do is remove that person's data from the training set. But we already discussed there is a lot of information that has been imbued within the network, which is much harder to take out. And this is what machine unlearning, the entire application of machine unlearning does. It tries to unlearn what has been learned based on a single data point. And it's not easy to do something like that. So this is, again, an intervention, which is you are intervening within a trained neural network to remove certain information based on aspect. There's, of course, other things as well, which is machine attacks or inferential attacks, essentially. We'll talk about that in a little bit. The next field is interpretability. Now, generally, this is used when we talk about evaluating explanations. When we evaluate explanations, the way we do it is we mask a certain region, pass it through the neural network again. So you've created an out-of-distribution data and now passing it through the neural network. Right? Or when we talk about introspective learning, we use these features of explanations to train a model and used it in order to construct a more robust thing. So instead of explanations becoming this kind of a post hoc field where I'm just explaining my results, you're using it now in order to create more robust decisions. So you're intervening within your network, your decision based on something that you would have learned later down the line, which is post hoc. Prompting, probably the easiest one to understand what interventions are. Given a ChatGPT model, you can go in and ask a question. So you're intervening within a network and asking it a certain question. Hopefully, you want to get some answer out of it. So this is an intervention from a network's perspective. Let's say you have asked it 5 questions, and now you want to change your second question based on what it has told in the 5th one, right? So this is when you intervene and ask a different kind of a question, or you restate your second question based on a different 5th question. So this is where the prompting aspect comes into picture. The last one is something that has, which is benchmarking. And this is something that we have done from the very beginning of deep learning analysis, where we train on a pristine data set and then try to test it on more difficult out of distribution adversarial, all these data sets. So you would have intervened in the the testing data and try to analyze the robustness or the sensitivity of your particular model. So this is also an intervention where you're intervening in the benchmarking aspect of your network itself. Now, it might seem that everything I've talked about intervention is a good thing, but it's not the case. The simplest way of thinking about it is if you're using ChatGPT, you know that there is some bias. Gemini, or I'm using ChatGPT more as colloquially, since all of us are probably aware of it, but any large language model out there, you know there is some amount of bias that is associated with it, or initially at least there was a lot of bias. These days it has been toned down, and generally if there is difficult question, it does not give you an answer. But generally in the beginning there was a lot more bias that was associated with these kind of models, right? So which implies that not all interventions are positive. There are some kind of negative interventions as well, and there are certain applications that describe what these negative interventions are. The first one is membership attacks, membership inference attacks. So basically you can get back your training data by looking at what the inference or the outputs are, which is not good. Especially think of it from a healthcare setting. Your personal information, your private information, we can get that back if it's part of the training data. We can reconstruct that data, either as tabular data or your scans or something like that, based on something called membership inference attacks. It's based on having millions of inference by changing small amounts within your data in order to reconstruct your data, especially within generative modeling. So in this case, interventions are negative. Again, the goal of this particular section is just to suggest that interventions can be negative as well. It's not always positive. We've already looked at adversarial images. This is a negative intervention. We look at the parameters of the weights and engineer certain noise which changes or which makes sure that this particular parameter will give you a different output with a very high confidence. So this is basically a negative intervention within the network. The last one is my favorite, which is this idea of prompting. This is an intervention that comes across due to just ignorance of the way models are defined. So, or maybe ignorance is the wrong word. The aligned purpose does not exist between the model and not. So let me go through this example here on the left-hand side. So we look at a particular image and we ask a human being. So this is from something called Segment Anything model, SAM, which was released last year by Meta. It can segment anything. So in this case, we wanted to segment a baseball bat. Now, a person went in and clicked on this. The way it works, SAM works, if you haven't tried it, I would advise you to. It's a very nice model. It's available on Meta's website. So if you go and put a green point, which is an inclusion point, it basically segments that region. And you can then put a red point and leave that region out. So initially, some person started off with B here. They put this kind of green point here, you see, and there is a green point here, which implies that the bat has been segmented correctly. It had a mean intersection over union of around 0.55. And then they thought, okay, I can increase it more. And they went in and started adding more points. So they added I don't know if you can see, but there's a red point here, which is an exclusion point, which basically says that anything here, you have to include it within your segmentation. But at this point, you need to exclude it from your segmentation. Now, SAM, the way it works is that it has this positional encodings. It's a transformer, it has positional encodings. So as soon as you click somewhere, even if it's a negative one, it tries to see everything within the area. And then it says, oh, you know what? This white color here kind of is similar to the white color over here. So let me remove this region from my segmentation, which is essentially what you see here, right? There is a huge decrease within your IOU. The intention of the human being is, of course, very clear to us, which is they want to make sure that the intersection over union increases. You want to make sure as much of a better segmentation as possible. But the aligned purpose initially that we were talking about with respect to your stop sign, your bottom hand corner and so on, does not exist within these models. So what happens then is that even though the purpose of a human being in putting this kind of a red dot is good, it does not translate into a good output, essentially. So again, this is an intervention. The goal is good, but the purpose, and because human beings don't understand the operation, how a neural network works, users don't understand it, it's not always going to be good. Any kind of some interventions are going to be negative. So that's why we call this almost like a trial and error intervention. And this is true for all prompting cases, language as well. You go on ChatGPT, this is all you do. You go through, you ask a question, you're hoping that there's a chain of thought commands that you're giving to a neural network, and that chain of thought leads you to the right result. But in many cases, that is not going to be true. And in fact, you're going in the opposite direction. And the worst part is that usually a SAM gives, this segment annealing model gives you a score. And what you see here, the score is basically like a confidence of how much it thinks you've made the right decision or you've made the right prompt to give you this one. So this score is going the opposite direction. So when this increases more, your score has increased. So during test time, a person do not have access to this IOU. They only have access to this score. So essentially, it's leading them in the wrong direction. More and more prompting you do, it's going in the opposite direction overall. And this is where the intervenability, the problems within intervenability exist, right? Or the negative aspects of intervenability exist, which is that the operational limit, we don't know it as users. This is trained by Meta on more than 1 billion masks, billion segmentation masks. We have no idea about many of the things that exist within the network, the engineering aspects of it, why they chose a certain architecture, a decoder, and so on. So we are just using it. And when we are using it, there are going to be problems that are associated with this intervention. So this is a data set we recently released at CVPR, which has these kind of problems or interventions which are incorrect. Now, let's talk about certain mathematical attributes. One of the reasons that this is hard, intervenability is hard, is because there's not as many mathematical frameworks that allow us to study it. The one that you will all be familiar with is, of course, the causal analysis. But causal analysis, as I mentioned before, is quite straightforward. Is easier to understand when it's tabular data and you have a structured causal model, a graph basically between causes. But that is not there within large data sets or within image data sets. So generally, when we do causal analysis, there's something called Juraya Pearl, back in the 90s, had this amazing set of do calculus framework. And the goal of do calculus is to assign a certain causality to all factors. And in this particular case, there are 3 rules that are used for causal analysis, and it fails for us in the first causal rule itself. Let's say that I want to construct a causal analysis for the spoonbill, and I'm telling you that the cause of that this particular image is assigned a classification of spoonbill is because of the beak. In other words, I'm telling you that a beak is necessary and sufficient in order to classify a spoonbill, which implies that I can take a spoonbill beak, put it on an elephant, and it should be able to classify it as a spoonbill. Right? This is essentially what rule 1 of causal analysis implies. The statement that I made, where a particular factor is the cause, is something that we are now going to assign based on causal analysis. And if I tell you that the beak is the most important, I can put this here, and I need to be able to say that this is a spoonbill. Of course, doing something like this is not possible in these kind of large scale data sets on these kind of images. If it was a tabular data, I could change a 0.5 to a 0.6, and then I could look at what the output of a structured causal model was. But I don't have that luxury here. Images cannot easily be transformed. Of course, I can use multimodal, a large model essentially to generate an elephant with a beak, but still, it would still be out of distribution from the model's perspective. So you will never be able to get a good causal analysis out of it. The second rule requires that you need to make other kind of interventions within the framework. So by saying that the beak is the most important one, I'm now telling you that the leg is not as important. So I should be able to delete it here, or I should be able to add it here, and it should not make much of a difference within my analysis. So maybe I'm just beating a dead horse in this case, because if rule one we cannot perform, rule two again is not something we can perform. Same thing in rule three as well. Now we need to move away from the peak and now look at different factors and so on. So all these three rules have to be satisfied in order for us to say that certain intervention is a good intervention, or it's something that we can analyze. And it's not possible to do this kind of an intervenability framework. Now, the last three slides might seem more like a toy example. It is, in fact, a toy example, but these rules and these kind of analysis is something that is followed in explainability evaluation and in constructing explanations. So there's a very famous method called RISE, which is randomized input. I forget the exact name, but RI is randomized inputs. So the way RISE is constructed is we construct these masks. What you see over here, masks, where many of the regions are randomly masked or black, and they are multiplied with the original image, and you have Hadamard product between the original image and these masks. You pass this through a network, you look at what the outputs are going to be, and you use these outputs in order to now create a weighted sum between the masks and the outputs and create this kind of an explanation. So this is something called a perturbation method. And the reason this method is very good and popular is because in GradCam, you need to have access to gradients, let's say. You need to know the internal workings of a model. In this case, you can treat the model as a complete black box. You don't really care about if it has a convolution layer, fully connected layer, task specific, nothing. It's just a very simple model. All you need is perturbations on the image, and then you have the outputs. Technically, I think you take about 6,000 different masks in order to create these kind of explanations. So RISE is a good method, and this mask that we see here is kind of similar to rule one, where you're masking a certain regions within the image. You're looking at what the output is. Of course, after that, you're using it as a method. So you're just multiplying 0.09 with the mask, or whichever probability it is, and you're getting a weighted sum, right? This year at ICME, we showed a very similar algorithm where instead of looking at something like outputs, which is the logits or the probabilities of predictions, if you just subtract it from the original probability, use that as a weighted sum on the masks, you get a very different kind of an explanation, a very bad explanation for the same image. The problem is that based on the explanation evaluation metrics that exist, this shows a higher rating. And this is not just for a particular one image. Across the entire ImageNet validation set, this kind of a bad explanation gets a better score than before. The reason is that we don't really understand all possible interventions, and we're just using these interventions. We are using 6,000 different masks, but think about the kind of interventions, number of interventions that can happen. In each pixel, it might range from 0 to 255, right? So an intervention is basically a 128 pixel becoming a 129 pixel. So that is one intervention, or it should be one mask. 128 becoming 130, that should be another mask, and so on. So there are infinite possible interventions, and we are only using 6,000 to make these masks. So essentially, by changing a small portion of this, we can create these kind of adversarial explanations, which is it's more of an adversarial explanation, and the mask is very bad. The explanation looks very bad subjectively, but objectively, it's apparently a very good explanation. And the reason for that is that we really don't understand the interventions, and we are using it within many of our applications. So it will become problematic down the line. So that is the danger of these kind of incomplete explanations for interventions from the perspective of causality. And this another framework that we can use is predictive uncertainty. Again, this is a little bit new as well. And there are problems with this. We'll discuss in a bit. But essentially, you accept that all interventions are not possible, and you say that every particular explanation has some amount of uncertainty with respect to it. So in this case, you have this as the explanation from GradCam, what you notice is that the snout is not as highlighted as, let's say, the jowls here. So in fact, in your uncertainty, you need to say that the snout is where you're uncertain about and need to construct the mask on the right hand side. It's not just sufficient to give this kind of an explanation. You should also give an uncertainty at every single point, which is not good because you're saying that an explanation will answer certain questions, and now instead of just giving a certain explanation mask, you're also saying that there's an uncertainty involved with those particular explanations, and that is because that it's impossible to calculate uncertainty. Sorry, it's impossible to use all interventions in our framework, and we have to say that certain uncertainty is involved in this particular case. So this is a little bit newer work. It basically was accepted a month back, which is the study of intervenability in interpretability. So we call it voice, which is variance of induced contrastive explanations for quantifying uncertainty in explainability or in interpretability. But as I said, anything with respect to intervenability work is new. There's a lot of potential for people to go through and try to understand it a little bit better. But ideally, we want these kind of explanations where you don't just get an explanation, but you get a heat map of the uncertainty that is involved with that explanation. Now, the reason it exists is because of evaluation. The way we evaluate these kind of explanations is by masking and passing it through an image. So let's say I have two explanations. This is GradCam and this is GradCam++. This is taken from paper GradCam++. The way it works is you mask your original image based on explanations, pass it through the image and do it across like 50,000 different images and calculate the expectation. So you want to make sure that all the outputs are, in this case, spoonbill. Or whichever image that it belongs to, you want to make sure that that is the image that is given, even after the masking. It makes sense, right? If your explanation is telling you that the pink body is the most important region for making the assertion or the classification that it's a spoonbill, by masking out all the other regions and only keeping that region, you should still get the same correct prediction. So unfortunately, let's say in SX1, it's given the prediction becomes a crane, while in SX2, it still remains a spoonbill, which implies in this case that SX2 is a better mask compared to SX1. And this is like an objective way of saying whether explanation 1 is good or explanation 2 is good. So you take expectation across n images, and if your second explanation method gives you a higher expectation, that implies that explanation 2 is generally better than explanation 1. The reason we talked about it is that this is very similar to uncertainty definition. Predictive uncertainty is the variance of your output given certain perturbation, in this case SX, which is your explanation mask. And if you use some kind of a variance decomposition, it becomes variance of expectation plus expectation of variance. The thing is that anybody who has let's say you have a method which is explanation 2, the authors would have already made sure that this is 0. Your expectation of y given SX2, this part is going to be 0. So variance of this 0 is going to be 0. The reason they would have made sure of that is because they would have tested on their, on all the 50,000 validation images. They would have made sure that their expectations, let me go back, expectation of y given SX2 is going to be as 0 as possible. I'm sorry, this should have been here, where the variance of y given SX2 is going to be 0. Expectation is going to be very high, but the variance is, and because your expectation is high, your variance is going to be 0. So only one of these terms is going to remain in the outputs. So again, this has to be in the opposite direction. Your expectation is high, but your variance is low in this particular case. And this is an important observation, which is uncertainty in explainability occurs due to all combination of features that the explanation did not attribute to the network's decision. This is where we go back to the snout. Snout was not as well highlighted as the other parts of the explanation, right? So the question now becomes, why did it not highlight it? So if there is an intervention that would have highlighted the snout, it's not as much weighted as the previous ones. And this is where we have that particular result. So the effect of a chosen intervention can be measured as a negative of all other interventions that were not there, or we could not choose it. Again, there are infinite interventions in that shark image, but we only chose 6,000 interventions to create the rise masks. Infinity minus the 6,000, all those interventions have some effect related to it. And those can now be combined in order to construct some kind of an uncertainty map, right? So in this particular case, this map here is basically the effect of all the non-chosen interventions. All the interventions that I was not able to choose is what is creating this uncertainty map over here. So this is the framework of how, at least the one that we are advocating for. Causality is very hard. That's why we need to have an uncertainty framework to analyze these kind of interventions, which is based on non-chosen interventions. We cannot humanely choose any other or all possible interventions. So we have to accept that some kind of uncertainty is going to occur. The problem, of course, is that I just said it's infinity minus 6,000, right? So not chosen features are essentially intractable because there are infinite possible ways of looking at it. And this is where our output comes into picture. The formula we had before comes into picture. We are only interested in those interventions that changes the variance. So your V of Y given Sx has to change. Your Y the prediction from your network has to change. It needs to become Y1 given Sx1, Y2 given Sx2, and Y whatever given Sxn, right? So we are only looking for the interventions where the output prediction changes. And this is the contrastive explanation we saw before. Yp rather than Q, so Y2 rather than Y1 tells you the change required in my original input. In this case, it was for a box set, where the joules were different. If this change had occurred, then it would have been Y2, which is a boxer. So now we have access to all these contrastive explanations that we can now use to construct the heat map that we showed before. So given these n contrastive explanations, we need to take the variance across those n contrastive explanations in order to get our uncertainty map. So it's the block diagram is straightforward. It's exactly what I mentioned. This essentially is a contrastive generation example. And given all these contrastive maps, you can get your outputs. Of course, you may choose the number of contrastive explanations that you want, depending on the top K predictions, or you can do across 1,000. You'll still get very similar results. Empirically, we have seen that at least on ImageNet dataset, across all 1,000 gives you probably the best results, but in different datasets that might differ. But essentially, the method is the same. It's a variance across these contrastive explanations in order to get these kind of uncertainty maps. In order to get these kind of uncertainty maps. So why is this good? Because at the end of the day, we need to decide on a few questions. I need to ask the question if GradCam++ is better than GradCam, and I need to ask the question that a SWIN transformer, is it better than something like a VGG16 architecture or an AlexNet architecture? And the goal of any intervention that we do is to answer these kind of questions, at least in the case study of interpretability, right? So what we generally notice is that on correct predictions, so let's divide our qualitative analysis into correct predictions and incorrect predictions. So what you notice here is the correct predictions. Given this mosque, the reason it is specified as a mosque is because of the dome structure that you see here, right? GradCam shows that it's the minarets, basically, while GradCam++ shows that it's both the dome as well as the minarets that is telling you that this is a mosque. Ideally, you don't want to be uncertain about the same region that you're using in order to make the prediction, which you see in the incorrect prediction. You see here that the explanation of this dog, I think this was a sled, overlaps between uncertainty as well as the explanation. So in other words, what this is telling you is that the same region that is used to make the prediction is the same region that it is uncertain about. This reduces the trust that you need to place within the explanation module for this particular neural network, right? So that is essentially what you see here. Of course, these are more examples where we know that it's correct and incorrect, but this is true across any given explanation, even when you don't know if something is true or not true. This is how you would define, let's say, a trustworthy measure, using your uncertainty as well as your explanation in order to construct this measure between the two things. Same case with here as well. This bakery was also incorrectly predicted. And what you'll notice is that, at least in GradCam++, it's more clearer. The same region that is used for explanation is now used for uncertainty as well. In fact, and if you look at this was a correct explanation for the bald eagle. For GradCam, you'll see that it's uncertain about regions around the region that it is most certain about. So you can calculate some kind of scores between them, in this case, a mean intersection over union between explanation and uncertainty, in order to get the best kind of uncertainty between the two things. Now, another metric that we can use is signal to noise ratio, or SNR. In your correct explanations, most of your heat map is very localized. But with these kind of incorrect explanations, your heat maps is not as much localized. So you can use that in order to now construct a metric, saying that, oh, Swin transformer is probably better than your VGG16 based on the explanation as well as the uncertainty. So that was more of a case study within intervenability. And now the idea is basically to say that the residuals of this interventions is essentially your uncertainty, and you can use that as a framework to analyze and understand interventions. Next few slides are just that we are just listing a few benchmark data sets that are out there. There's CureTSD, CureTSR, ImageNet-C. This is something we showed before. ImageNet-P. There are a lot of benchmark data sets that we can use to say whether something is a good network or a bad network. I encourage everyone, again, the slides are present online. Even the last slide will have a QR code. You can use that. All of these are present online. All these data sets are something that you can use. CureOR, as well as the ProPoint prompt data set that we just showed. So that brings us to the end of the tutorial. So I think we had time till around 5 o'clock. So again, since I'm the only person doing today, I think I've sped up a little bit more in the final stages, but if anybody has questions, you're more than welcome to ask me or email me down the line. Conclusion section doesn't have a lot. It's usually more memes, essentially. This is something that we had shown before. It's not always clear when and where to use novel data. We should not use it during training perspective. One, because we won't have access to it. And two, as I showed before, there could be catastrophic forgetting, or there might be information retrieval issues, which ensures that we don't know how and when to use these data points. Whenever we deploy our models, we think that during testing, it gives us the best possible results, but we will come across stuff during deployment that it's really, really hard to get our results. Adversarial images are one such thing. It doesn't matter what kind of let's say outputs or how good a network is, you can always engineer a good adversarial example to make sure that the results are very, very bad. There's a lot of work that goes into optimization, a lot of work that goes into data collection, but not as much in research related to the inference. And these days, with the advent of foundation models and access to these models by users, it's very important for us to look through and try to understand inference methods as well. Instead of just looking at the YP questions, if we start looking at YP rather than Q and what if questions, there's a lot more things that we can understand. The aligned purpose thing that I was mentioning before with respect to having this kind of why no left rather than stop sign, and you had the bottom left corner as highlighted, is something which is very, very important for us to look through. And you won't get that by just looking at YP. You have to have a YP rather than Q as your thing. And in the very end, we saw that explanations have a lot of uncertainty associated with them. So just having explanations is not sufficient. you need to have a lot of uncertainty, or you need to have uncertainty masks with respect to these interventions, or sorry, with respect to these explanations as well, just because of the fact that interventions are not always understood by human beings who actually utilize these kind of models. That brings us to the key takeaways, and it is about the role of gradients, which is that gradients provide us with this kind of Fisher information. And this Fisher information is a relativistic information measure. It shows us the relationship between the model theta and the output that can exist and the input that gives that output. So without knowing anything about the model, we can use gradients to extract certain properties about these manifolds. We always make certain assumptions, of course, that it's a Gaussian distribution, and so you need a variance and your theta. But based on those distributions, you can know something about the underlying model, even during at inference. It can be used for a large number of image understanding applications. Again, the reason being that it gives us local information and directional information, and we can use that for adversarial detection, out of distribution detection. I didn't talk about open set recognition, but you can do it with those applications as well. There's a lot of applications that we can use gradients. In terms of future directions that we can use, I've listed about 4, but I don't believe that this is all of them. In fact, this is probably something that I would be most interested in, which is the idea of test time augmentation. Let's say we have a good understanding of inference. Maybe we need to have this kind of let's say we are doing some kind of a face recognition. When we do it on the phone, if it doesn't work once, we try again, but this time move our head down or move our head up, right? If a network is going to tell us, it's also, your face recognition is also dependent on some neural network. If it can tell us that move your head down by 30 degrees, that is essentially what we want from a neural network. So that's a test time augmentation. And the result of the network saying move your head by 30 degrees downwards is active inference. It's basically the network knows what it wants and it's asking us exact data that it wants. And during inference, I think that is something that could be very, very impactful. This kind of research, which is active inference. And of course, uncertainty in explainability, label interpretation, and trust quantification. The problem with something like medical imaging, for instance, is that the outputs are not always known. You have a team of doctors who come together and they tell you what the output is going to be, instead of one person deciding what the ground truth is. You need an uncertainty with respect to that as well. So we usually have data uncertainty, aleatoric and epistemic, which is data and model that we saw, but we never have an interpretation uncertainty. Ground truth also has certain uncertainty involved with it, where each doctor, let's say, is going to say, oh, there are cancer nodules in this particular place, cancer nodules in this, and then there's an arbitration process, and then they decide what the ground truth is going to be. So there has to be a different kind of uncertainty, especially during the inference process. And of course, there's test time interventions for AI alignment. This is exactly what we talked about before, which is we want an aligned purpose between a model, the way it makes its decision, and the way humans make their decision. That has to be consistent. Of course, yes, if there is no aligned purpose, a network may have a better accuracy, but it's not as important at deployment. You want to make sure that the aligned purpose actually exists so that humans can use it safely. That brings us to the end of the tutorial. And again, the references, it's all listed, all the references that we talked about, and the material is available online. So if you're interested, we showed this in the beginning of the session as well. So if you're interested in the slides, it should be available. So that brings us to the end of the tutorial. Thank you for staying through. I know it's been like 2 hours, 47 minutes. So thank you. Yeah, if you have any questions, you're more than welcome to stay behind and ask me. Otherwise, I don't know, hopefully there's a little bit more coffee. At least I think I'll need it for sure.